demand, and at the same time, the supply of energy is very efficient, is very good. Means the gram fuel, for example, needed to produce 1 kilowatt hour is very low. Then we talk about state of the art in terms of efficiency. Yeah, just imagine a very, very light vehicle powered by a very efficient powertrain. Very little kilowatt hours needed to run the vehicle, and very little fuel grams per kilowatt hour needed to supply this amount of energy, kilowatt hours. This is then considered as state of the art in terms of efficiency. This would be the best thing to do. Come with the demand of energy down and supply the remaining energy in the most efficient way. But there are also different scenarios. Yeah, for example, the demand of energy could be still very, very little, but the powertrain is maybe not state of the art. The powertrain is maybe a very cheap gasoline engine, maybe even without a turbocharger or something. Therefore, the gram per kilowatt hour needed to make this engine run is high. In a second, but still the kilowatt hours in order to cost by the vehicle are little. Then it's maybe kind of cheap subcompact. Yeah, very, very cheap small car. Supply and recovery has a very little driving resistance, but if it's powered with an old engine, then this is maybe still not state of the art in terms of efficiency. There are also different scenarios. For example, you could imagine a very efficient state of the art powertrain, maybe kind of latest plug-in hybrid or something, but still a very high energy demand. This could then be a brand new SUV. Yeah, for sure. If you are asking for a big car, lots of space, lots of comfort, lots of systems like seat heating in winter times and massage, and for sure air conditioning and so on, then the energy demand may be high. But if such a vehicle is powered by latest powertrain, then the overall consumption may be still not extremely high, at least. And then there is also for sure the worst case scenario here included, if you have a very high energy demand, but also a low efficient powertrain, then this could be maybe something like an aged van or something, which is then the worst thing to do. Now I would like to know from your side, why is it that important to distinguish between demand and supply? What do you guess? Here you can see the formula. Yeah, in the end, it's about fuel consumption or the consumption of electric energy. And if you're talking about fuel consumption, then it's not about liters, but it's actually about grams. So how many grams fuel do you need to cover a certain distance with a specific vehicle? And this one comes with the efficiency, the gram divided by kilowatt hour needed from the engine, multiplied with the kilowatt hours caused by the vehicle. Why do you think it's that important to distinguish between the two dimensions? Can you still hear me?
Yes, we can.
Okay, great. So I can also ask in a different way. Yeah. So if I tell you a specific vehicle needs 20 liters per 100 kilometer, can you judge on it whether it's good or bad?
No, you would need more metrics to pass judgment.
Yeah, sure. So what do you need to know?
So you know the demand, but you don't know what kind of supply that vehicle has. So it could be a good supply or bad. So
Yeah,
they depend on each other for a better fuel consumption.
Yeah, maybe I support a little on that. Yeah. So 20 liters per 100 kilometers would be very, very good if you're talking about the heavy duty truck, right? So if you're
Yeah.
talking about the Mercedes Actros, for example, yeah, then 20 liters per 100 kilometer would be a very, very good value. If you're talking about the Golf, for example, Volkswagen Golf, then 20 liter per 100 kilometer would be a very, very bad result, right? And this is why we really need to distinguish between demand and supply to also check where we still need to improve, right? So if the demand is very, very little, if the car is very, very light, has a little number of auxiliaries in use, and you even drive very very calm, let's say. But anyway, need a lot of fuel to make it run. Then for sure you need to focus on the powertrain. Then you need to consider how to make the powertrain, the engine, the gearbox, and so on more efficient. This would be then the right thing to focus on. Yeah. If the powertrain, on the other hand, is already very, very efficient, you have the latest powertrain in use. But anyway, the consumption is very high, then you must further consider how to reduce the energy demand. Yeah, how to make the vehicle more light, how to make maybe the auxiliaries more efficient, and so on and so on. So this is why it's very important to distinguish between demand and supply. Yeah, you cannot judge whether 20 liter per 100 kilometer is good or bad if you don't know about the actual demand, about the power caused by the driving resistances. Okay, so very, very important. Always distinguish between demand and supply. But the story is even more complex, let's say, as shown in this graph. So we will now step by step check what we can do in terms of sustainability, starting with a certain reference value. Yeah, the reference value, as already mentioned, contains two major things. Yeah, first of all, the energy consumption of production and disposal, and then the higher portion, depending on the powertrain for sure, of the usage. If you're talking about the efficiency, we can also increase the efficiency of the production. Yeah, for sure, we can go for more efficient production technologies. This is very, very important for battery electric vehicles, as we already know that the manufacturing of the battery causes a lot of energy and therefore most likely greenhouse gas emissions. And we further need to reduce the energy in the use phase. And for this, there happened already a lot of things, as you maybe know by your own. So since the 1970s, the fuel consumption of German cars already went down to the half. So in the past, there have been already lots of achievements. Yeah, in the 80s, in the 90s, maybe you know that powerful vehicles with, let's say, 200 or even 300 horsepower. They used a lot of fuel, 10, 15, maybe even 20 liters, mainly caused by inefficient powertrains. And nowadays you can easily run a 200 or 300 horsepower vehicle with less than 10 liters. So if you go for a very powerful diesel engine, then you can definitely ride such a vehicle with less than 10 liter per 100 kilometers. So therefore, already many things happened, but for sure the story goes still goes on. Then you can see on the right side the let's say general system, how to assess the actual efficiency of a vehicle. As already introduced, it's about three main steps. It's about demand, supply, and recovery. And the supply of energy, again, can be subdivided in storage, conversion, and transmission. So this is the rough system we are talking about. I will also give an example. Yeah, for a battery electric vehicle, for sure, the storage is the battery. Then the energy conversion is done by the e-motor, and then you have always kind of transmission. You have a gearbox. You have maybe a differential. You have some shafts, and so on, to bridge spatial distance, and to maybe also transform the energy in terms of RPM and torque, or when it comes to the transmission of electric energy, the voltage and the current, and so on. And this is then the whole system of supply. The sequence must always be the following. This is very, very important. Yeah. First of all, before considering anything else, it's about minimizing the demand of energy. First of all, you need to consider how to again make the amount of required kilowatt hours to run the vehicle as little as possible. Yeah. For example, reducing the weight of the vehicle, reducing the air drag of the vehicle, reducing the power demand of auxiliaries, and so on and so on. So this one must be always the very, very first step, reducing the demand of energy. Then the second step is to go for the most efficient supply of energy. Yeah, to go for the most efficient energy conversion, mainly of relevance for internal combustion engine. Yeah, you know, the efficiency of internal combustion engine is comparatively little. It's maybe 1/3 or something. For sure, if you only operate in the best conditions, then it's higher, then it's maybe 40-45% or something. But as the operation of a vehicle is highly volatile, you also face different operating modes, and therefore the average efficiency of internal combustion engine is comparatively little, as I said, approximately 1/3 or something. Again, second step, make the supply of energy most efficient energy conversion, most efficient transmission, yeah, most efficient gearbox, most efficient, or let's say most slippy gearbox oil, for example, and so on. So this must be the second step, yeah, most efficient supply. And anyway, so even if the supply is already on a very, very high level regarding the efficiency, there will be always some potential left for recovery. And this must be the third step. After minimizing the demand, after optimizing the supply, the energy management must consider how to recover the inherent losses. So which one could be this? Can you imagine which energy can be recovered?
Kinetic or heat energy?
Sorry, I didn't get it.
Heat energy.
Heat? Okay.
Yeah.
So which heat in particular?
Could we
So where
use
can I get the heat?
The heat from the brake pads and stuff like that.
Yeah, but I think you cannot really recover the heat of the brake pad, right? So how could you transfer the heat from the brake pad to somewhere else?
in case of electric motors from the engine as a generator.
Okay, so
from the
Mhm.
engine.
Can you
Back
be maybe
EMF
more?
and everything to do with it.
So can you be maybe more specific? So 2 questions. Yeah, first question. So where can I get the heat from? And second, for which purpose do you use it?
Could we just use the heat to heat up the rest of the car, as in the interior?
Okay. Yeah, that's right. So as you know, if the efficiency is less than 100%, as it's the case for internal combustion engine as well as e-motor, yeah, there must be kind of waste heat. There must be kind of coolant or something to get rid of the lost energy. Yeah, and this energy, yeah, of the coolant, of the hot coolant, could be used or is used actually to heat the interior. Yeah, so you don't generate the heat extra, let's say. If possible, you use the hot coolant to transfer the heat to the interior and to heat the interior. Very good. What would be another example for recovery of energy?
Could it be the back EMF when the electric motor's running and then you stop applying acceleration, so it will still be running, but the engine itself is not putting any more power into the input of current?
So honestly speaking, I didn't get it, at least not fully, but it goes in the right direction, I guess. Yeah. If you need to decelerate the vehicle, yeah, if you need to brake, let's say, then there are 2 options. Yeah, you could use the actual brake, yeah, the brake pad, the brake disc, but then the whole mechanic energy of the vehicle is turned into heat. Yeah, you just heat the brake pad, you just heat the brake disc, and then both are again cooled by the environment, and the energy is lost. Then there is no recovery. If you instead use an e-motor to decelerate the vehicle, or to gain back potential energy, elevation energy when riding downhill, yeah, then this energy is again turned into electricity, can be used to charge the battery, the storage, and later on reused to run the vehicle. So this would be 2 options for recovery. First one is recovery of waste heat, of the heat inside the hot coolant, and the second one, if you brake not with the actual brake, but with the e-motor to again generate electricity. So once again, first of all, minimize the demand. Second step is optimize the supply, and last not least, there will be always some losses, and then we should think about how to recover these losses. Okay, the next slide now shows a very, very interesting fact. You can see the energy demand in kilowatt hours per 100 kilometer on the y-axis, and on the x-axis you can see the velocity. And I guess everybody is aware of the fact that the energy demand rises if the velocity of the vehicle, if the speed also rises. I think this is quite clear. Due to the air drag, it even rises very much with the increasing speed. But what you can also see in this graph is that the energy demand rises even if the speed goes down. Yeah, you can see the minimum energy demand is, yeah, let's say around 15, maybe 20 meters per second. And if you accelerate, the demand goes up. And if you decelerate as well, even more dramatic. Do you know why it's like that? Can you imagine what is the background for this?
Is it the energy input going into stopping the vehicle, so into the brake pads?
No, this has nothing to do with a brake pad or something. This is a constant speed, even. Yeah. So
Is it
once
to do with
again,
the pumping losses?
no, this has nothing to do with the pumping losses. We're talking about the demand. We're talking about the energy demand. So again, we need to distinguish. There is in this chart here, there is no engine in. This is just the energy demand. This has nothing to do with the supply.
Energy to break the inertia of the vehicle.
No, there is no brake because it's a constant speed. Yeah, just imagine the riding constantly with, let's say, 15 meters per second. Yeah, you can see the mouse, it's here. And then you compare this constant ride with, let's say, 5 meters per second, another constant ride. And you can see that the energy, even though the speed is lower, the energy demand is higher. How can this be?
Excuse me, sir. I believe it takes more energy to start the car and get it to higher speed. That's why the energy demand is higher at a lower speed.
No, there is, as I said, there is no deceleration, but there is also no acceleration. This is a constant speed. Yeah, just imagine you're riding with 5 meters per
Is it
second.
simply to do with the time that it takes?
Sorry, once again.
Is this to do with the fuel burning in it?
This has nothing to do with the fuel burning because I said it's about the energy demand. It's about the demand of the vehicle. This has nothing to do with the actual powertrain used. We are talking now about the demand caused by the driving resistance and the auxiliaries. We are still in the first step. It's about the demand and not about the supply. Demand, yeah, it's quite clear, right? It's the driving resistance and the auxiliaries. And the supply is then about the engine.
Maybe due to the friction?
Sorry, once again?
Due to the friction?
No.
The friction on the roads?
The friction gets higher if you're running on higher speed and gets lower if you're running on lower speed. I can explain to you.
Okay.
Actually, it's very simple. Yeah. So if you run at lower speed, yeah, then you will need more time to reach a distance of 100 kilometers, right? So if you just go for half of the speed, then you will need double the time to reach 100 kilometers, right? Do you agree?
Yes.
Yes.
Yes, very good. And then the auxiliary consumers also need to run double the time. So if you, for example, if you consider air conditioning, for example, yeah, then this one can have, let's say, 3 or maybe even 6 kilowatts, for example, yeah. And if you run then double the time, then you also need to run the air conditioning double the time. And this is why at low speed, the energy demand goes up very much because of the impact of the auxiliary consumers. So if you're riding in the city center, stop and go, and so on, then most likely the energy demand of the auxiliary consumers, like the air conditioning, like the HiFi system, maybe even, and so on, may be higher than the energy demand of the caused by the driving resistance. So this one is very interesting graph to talk about. So when you go for lower speed, then the energy demand might be also very, very high. And this is by the way also very important for autonomous driving. Yeah, if you add lots of sensors, lots of computers in the end to the vehicle to gain and process all the data to make the vehicle autonomous run, yeah, then this one gets even more severe because then you add again lots of auxiliary consumers. which have a very high consumption at low speed, and therefore the energy demand of the vehicle running at low speed also goes up a lot. Okay, here you can again see some figures for the carbon dioxide emissions of the BMW cars. And I already mentioned that in comparison to the 1970s, the consumption and therefore the carbon dioxide emissions went down by more than the half, and this trend continued in the past years for sure. So in comparison to the year 2000, we went down from roughly 200 grams per kilometer to roughly 110 grams per kilometer. So still, or let's say, already lots of achieved, but still a long way to go to meet the demands of the legislation, especially in the European Union. Okay, now we were talking about the efficiency of the vehicle. We were talking about the 3 steps: minimizing the demand, optimizing the supply, and then recover the remaining rest. But there are still some more things to consider. The next thing is consistency. And this one goes to the energy carrier. When it's about carbon dioxide emissions, then you could reduce them even to 0 if you use different energy carriers. So when we're talking about a battery electric vehicle, you could use green electricity. If you cover the whole demand of your vehicle with electricity produced by windmills, then there is no carbon dioxide involved in the whole process, and therefore the approach must be also considered as sustainable. But it could be achieved in the same way with internal combustion engines. So if you use a biofuel, for example, e-fuels, then there is also no net emission of carbon dioxide to be considered, and this one for sure also applies to the production of the vehicle. So if you use only green energy for the production, then you have also a high contribution to the sustainability. And this approach, to just replace the energy carrier in this case is called consistency. First efficiency, then consistency, and last not least sufficiency. So if you just avoid producing and using vehicles, then for sure you have no energy consumption and no emissions caused by that. And actually, in this moment, we already go for sufficiency, right? So I did not travel to London. We meet online, and therefore I have caused no carbon dioxide emissions by traveling, by using a car or using an airplane, maybe in this case. So the related emissions go down to 0. But to be fair, you should then also consider the energy used for the computer now, for the server infrastructure, and so on and so on. So this one must be also considered. But if you just avoid running a vehicle, then for sure the energy goes down. And there's also a different approach related to the mobility mode. So if you go for car sharing or carpooling, then your individual energy consumption, the energy consumption per capita also goes down very quick. So this is, I think, something very simple to understand. So if you run your vehicle to transport just one person, then the energy consumption per capita for sure is double that high as if there are two persons in the car. Okay, now we were talking a lot about efficiency, but the full scope of energy management also have different so-called target functions. Yes, things that should be impacted in a very positive way. First of all, again, the efficiency. The second one, ecology. This one is related to the emissions of air pollutants, and both the target functions of efficiency and ecology are mainly driven by legislations. So the authorities worldwide, they have limits for carbon dioxide emissions and therefore for efficiency, and there are also limits for the emissions of air pollutants. This one comes with the target function ecology. But we also have to consider our customers. Our customers are anyway asking for dynamics and comfort. And last not least, we also need to respect physics, and the physics is relevant for the target function of protection. So in total, energy and thermal management must cover efficiency, ecology, dynamics, comfort, and protection of the components used, of the materials in use, and so on and so on.
Excuse me, sir.
Yes.
Go back to the previous slide.
Sure.
Why is comfort placed under customers and not manufacturer?
Yeah, at the end, the vehicles, they need to fulfill the requirements of the customers, right? And the customers, they are asking mainly for two things, for dynamics and for comfort. Mainly thermal comfort of the interior. And on which of the target functions you focus on depends on the segment of the vehicle. Talking about comfort, then a luxury sedan definitely puts the focus on this topic, and therefore, for example, the air conditioning. When we are talking about a sports car, about a Porsche, then the focus is maybe not so much on comfort, but more on dynamics, and therefore power, acceleration, and so on and so on. When we're talking about another car, about a BMW i3, for example, then the focus is maybe not that much on dynamics and maybe not that much on comfort, but more on efficiency to achieve a very high range of the vehicle. So actually, every vehicle somehow deals with these 5 target functions, but depending on the segment, there is always kind of focus, because you cannot fulfill all the target functions at the same time maximum, right? So there must be sometimes some trade-offs, and these can be seen here. You can see on the left side which target function is prioritized and which target function on the right side here can be maybe then not fulfilled 100%. So for example, if you want to focus on efficiency, and maybe neglect a little bit the comfort, then you can introduce an eco mode of the air conditioning system. So if you're not asking for the maximum air conditioning, then you prioritize the efficiency and maybe not fulfill the comfort 100%. Another example would be if you prioritize dynamics, then you could maybe decrease the power of the AC compressor, again of the air conditioning system, to release the full power of the engine to the propulsion. So this one would be maybe done for a sports car, for a Porsche, for example. Maybe such a vehicle doesn't even have an air conditioning system. To save the weight and to also save the power for the propulsion only. And there are many additional trade-offs between the target functions, but you need to know that for sure it's forbidden to tackle ecology or protection. So that must be always ensured that the ecology of the vehicle is okay, that the air pollutants are after treated in the right way, and it's also forbidden to neglect the protection, to neglect cooling or something of the engine, because then it just will break down. Okay, let's talk about some more trade-offs. Very, very popular one is to prioritize the ecology. For example, or most likely after cold start of the vehicle. So after cold start of the vehicle, of the internal combustion engine, it's of a very high importance to quickly warm up the three-way catalyst. And this one can be done, we will talk about details later, by late ignition, fuel mixture enrichment, or electrical heating. And all such measures, they lead to a low efficiency after the cold start, so the fuel consumption will go up, but they prioritize the ecology to fulfill the requirements of the legislations. Okay, some questions from your side regarding this, regarding target functions and regarding trade-offs? If not, then we can move on. Okay. Now we can talk about the considered vehicles and powertrain architectures. As you maybe expect, for sure, the focus of the lecture will be on passenger cars. As you know, there are meanwhile many different segments available, starting with mini cars, going over to luxury cars, sport cars, and SUVs and so on. So many different segments available nowadays, and for sure the passenger cars will be in the focus of the lecture. But there are also some examples for commercial vehicles and motorbikes included in the lecture notes. So those vehicles, they have some specifics, and from time to time we will also talk a little bit about commercial vehicles and motorbikes. Then let's talk about which powertrains are covered by the lecture, and this one is shown by the diagram on slide 21. We have again 2 dimensions. So on the x-axis you can see the size of the electric motor and the battery, and on the y-axis you can see the size of the internal combustion engine. And if there is no electric motor, if there is no battery, we talk about conventional vehicles, ICE, internal combustion engine only. And on the other hand, if there is no combustion engine involved, then we're talking about pure electric vehicles powered by batteries and or fuel cells. And again, we will focus in this lecture on battery electric vehicles. And in between these two, let's call it extreme scenarios, there are meanwhile many different variants of hybrids available. So a pure ICE vehicle actually is no more state of the art. So at least some functions of microhybrids are nowadays standard for passenger cars. So at least for premium vehicles such as BMW passenger cars, all of them are kind of microhybrid. And this one can be covered by a 12-volt electric system. And then if you move on to mild hybrids, to full hybrids, to plug-in hybrids, then you need to raise the voltage of the electric system to still cover the power demand. And then this goes on to 48 volt or later on starting with the full hybrid high voltage systems. So this would then be the scope of powertrains covered by the lecture. And here you can see some more details for hybrid powertrains. Maybe there are actually, let's say 3 different types of hybrids. So the first one is a parallel hybrid. The second one is the second one is a serial hybrid. And the most extreme serial hybrid is a so-called range extender REX. So do you know what's the difference between a parallel and a serial hybrid?
So I think the parallel hybrid is directly connected to the wheels, while the serial has the battery pack away from the wheels, which is not connected to the wheels from the drawing.
I'm not sure if I fully got it, but I can quickly repeat. So the parallel, so for sure, hybrid always has 2 propulsion engines installed, right? So first the internal combustion engine, and second the e-motor. And if it's parallel, then both of these motors can power the wheels. You can power the wheels by the internal combustion engine, and you can also power the wheels by the e-motor. Then it's considered as a parallel hybrid. If you're talking about a serial hybrid, and this one can be seen here on the picture, then there is no option to power the wheels by the internal combustion engine, but the internal combustion engine is only used to generate the electricity to later on make the e-motor run. This is then called a serial hybrid. And what do you guess? What is the advantage of such a serial hybrid? Why would you do such thing?
Maximize the efficiency of the internal component.
Exactly. So if you use the internal combustion engine only for the generation of electricity, you can optimize this engine to a very narrow operating area, right? So you don't need to run on different speeds of the engine. You can focus on the most efficient speed and torque area, let's say. You also don't need to cover the maximum power demand of the vehicle. It's sufficient to cover the average power demand of the vehicle, and therefore the engine can be also smaller, therefore lighter. You don't add too much weight to the vehicle, therefore the driving resistance is minimized, and so on and so on. So this would then be the advantage of serial hybrid, of so-called range extender mainly. But we will also come to the details then later on the lecture. So this is now just the introduction to the general powertrains. Yeah, as you maybe know, BMW does not focus on one technology only, but BMW offers the so-called power of choice. And I have one example included in my notes. The current BMW X3 can be purchased in different with different powertrains. Yeah, you can have a diesel engine, you can have an Otto engine. Both of them are considered as micro hybrids based on 12 volt, and then you can also go for so-called XEV. You can have the very same vehicle powered by a plug-in hybrid, or even as purely electric battery electric vehicle. So this is the power of choice. Yeah, you can go for different internal combustion engine. You can have hybrid, and you can also have battery electric powertrain in the very same vehicle. And meanwhile, BMW also introduced mild hybrids based on 48 volt technologies, which are considered in between the micro hybrids and the XEV. Okay. Yeah, then we already talked about different hybrid topologies, means parallel and serial. And when it comes to the parallel hybrid, then you still must consider or distinguish by the position of the e-motor. Yeah, if the e-motor is in front of the ICE, let's say, if it's integrated in the belt drive, then it's called a P0 hybrid. If the e-motor is fixed on the crankshaft, it's a P1. If the e-motor is fixed between the clutch and the gearbox, it's a P2. If it's fixed on the transmission output shaft, it's a P3. And if you use an electric axle, yeah, for example, an electric rear axle with no mechanical connection between internal combustion engine and e-motor, then it's called a P4 hybrid. So question to you now, which one do you minimum need, or which one do you need to run the vehicle electric only? So if you're at low speed inside the city center or something, if you want to run pure electric, which parallel hybrid must be used?
P4.
Yeah, but there are also different options, not only P4. So can be, yes. Sorry, once again.
Or 2 and 3 as well.
Sorry?
P2 and P3.
P4.
Okay, yeah, very good. P2, P3, and P4. Because with the P0 and the P1, you will always also run the ICE when running the e-motor. Yeah, because you cannot decouple the e-motor from the internal combustion engine. And yeah, as I said, to run electric only, you need to use P2, 3, or P4. Very good, thank you. Okay, yeah, then let's quickly check the architectures of the different powertrains. I have some examples in the lecture notes included. I think you know about them already, but let's repeat. The micro hybrid, yeah, shown here, has got the combustion engine, yeah, for sure. Then the gearbox, yeah, the transmission to the rear axle, the differential, and then finally the power is transmitted to the wheels, and yeah, the wheels can be also or also include. Sorry, I'm looking for the English word. Yeah, on the axle there is also the brake installed. Yeah. Question to you now: do you know for which purpose you need the differential?
Come again?
So for which purpose do you use the differential?
To have different speed on each wheels while the vehicle is taking a turn or something like that.
Very good. That's right. Yeah. So if you turn around, yeah, if you go through a curve or something, yeah, then the wheel on the outer side must cover a longer distance than the wheel on the inner side, and therefore, as the time is the same, the speed must be different. And in order to achieve different speeds on the wheels, you use a differential. Very good. Okay, then here you can see one example for. Yeah, sure, anytime.
So why don't we have differentials at the front of the vehicle as well? Why is it only predominantly at the back?
Yeah, so for sure. So if you power the front axle of the vehicle, then you also need a differential there. But in this example, this one is a four-wheel drive, and then for sure you also need a differential on the front, but I haven't highlighted here. Okay,
makes sense. Okay, thanks, sir.
So for sure you only need the differential for the axle which is powered, yeah, no doubt. And in this case, in this example, both are powered, and therefore there is also a differential in the front, but I didn't highlight it. Okay. Okay. Then the next one is a P1 hybrid. As you can see, yeah, as already quickly introduced, for the P1 hybrid, the e-motor is mounted to the crankshaft. So in this case, the e-motor is assembled between the gearbox and the crankshaft. And yeah, as also shown here in this slide, the hybrid, the high voltage hybrid, usually offers some more options for further increase the comfort, for example, of the vehicle. In this case, there is a electric AC compressor in use. What from your perspective, what would be the advantage if you have an electrical AC compressor?
It can be run at different speeds.
It takes off load off the engine, and the engine can work more efficiently.
Yeah, but if it's not a plug-in hybrid, then the engine may be also used to charge the battery and therefore to run the compressor indirectly, let's say. But you already mentioned it can be run on different speeds. So can you maybe further explain? So what do you mean by this?
Well, if it's connected to the IC engine like it is normally, it can only be run at the speed that the IC, well, related to the speed of the engine. And that might not be sort of relative to the demand.
So the advantage is that the speed of the compressor is independent from the internal combustion engine, right? You can therefore run the compressor on the required speed and not on the speed which is given by the engine. And you can even run the compressor if the engine is turned off. So if the vehicle is parked, yeah, in summertime, you could independently run the compressor to cool down the vehicle without starting the internal combustion engine, and this is considered as one advantage for the comfort of the vehicle. Okay, next one is a P2 hybrid, and the difference in comparison with the P1 is that there is a clutch between the internal combustion engine and the e-motor, and therefore you can decouple the two from each other, and you can run the vehicle also purely electric when running on low speeds and so on. And in this pictures, you can also see the required components of a electric powertrain. So it begins with the charging socket, to plug in the cable to charge the battery. But this one does not go without a so-called onboard charger. The onboard charger turns the AC current of your plug at home into the required DC current to charge the battery, which can be seen here, the battery, and to then later on transform the electrical energy of the battery again into AC. You use the so-called inverter power electronics to finally run the e-motor. So these are the main components of the electrical part of the powertrain: the charging socket, the onboard charger, the battery, the inverter, and the e-motor. But we will talk about this then also in detail later. Here you can see one example for a P4 hybrid. This one.
So I have a question.
Sure.
Let's say in P2, the engine fails. Maybe the fuel gets finished. Can the electric motor power the car at its full speed?
No, most likely not on full speed. So for the plug-in hybrid, the power of the e-motor is limited to, let's say, maybe 80 or 100 kilowatt or something. So this for sure depends on the specific design, but you can definitely not run on full speed pure electric only. And also as you can see on the picture, the battery is quite a little, so you can also not cover a big range with the battery. Does this answer your question?
Yes, it does.
Okay, great. Yeah. On the next slide, you can then see a P4 hybrid, and the P4 hybrid works as follows. You've got a pure internal combustion engine driven front axle, let's say, and then the rear axle is driven by the electric powertrain only, and therefore, you can again run the vehicle purely electric as well. Then we have the range extender, also here shown on this slide. On the left side, you can see the powertrain of the BMW i3, the pure electric powertrain, let's say, and then you can also purchase as a special equipment an additional internal combustion engine, which is shown here, the so-called range extender REX, which is only used for generating electricity and charging the battery to increase the range of the vehicle. So the actual goal for sure is to run on the battery only, but if you want to cover bigger distances, then you can use this small range extender to generate electricity for the powertrain. Okay, 1.5 hours already spent, so I think it's time for a break now. So at least for me, to recover my voice a little bit, and then I will be back with you in 10 minutes. Okay, 10 minutes break, and then we will move on. Okay, welcome back. Can you hear me again?
Yes,
Yes, sir.
Professor.
Great. Yeah. Then let's move on with a pure electric vehicle with the BMW iX3, powered by the latest heat system. This one is a highly integrated electrical propulsion system, means the power electronics, the e-motor, the gearbox, the differential, the control unit for sure, as well as cooling and lubrication system is
Sorry, sir.
integrated. Yes.
The voice is echoing.
Can you hear me?
I can now.
You can hear me?
Yes.
Okay, great. Yeah, so the whole propulsion system, as shown on the right side, is integrated, highly integrated in one central housing. We will discuss about the details then later. The whole system is again integrated in the rear axle. So everything needed to run the vehicle is highly integrated in the rear axle. And then you still need the battery for sure, which is in the underfloor. So at the very bottom of the vehicle, which is good for the center of gravity. Yeah, as you know, heavy things must be put on the bottom to have a good dynamics of the vehicle. The only thing you then still need is the onboard charger in the front of the vehicle. And this is how the whole powertrain looks like. So the onboard charger for AC charging, as well as DC charging in the front, the battery in the bottom, and the propulsion system highly integrated, as I said, in the rear axle of the vehicle. So this is the architecture of the latest BMW iX3. Okay, we can skip this one. Yeah, as I said, we will not cover the fuel cell in this lecture here. Then the next slide then somehow summarizes the things already mentioned. In order to meet the requirements in different markets of the world with different legislative regarding ecology, efficiency, maybe also safety, and customers, which have requirements regarding costs and so on. The car makers must produce different variants of vehicles, as I said, starting from the A segment to the J segment. As well as different powertrains. So, for example, when it comes to the A segment, where costs are mainly to be considered, you will maybe choose a very simple and cheap gasoline engine. If you want to go for an internal combustion engine only. If you want to have some hybrid functions, then you can cover already a lot with 12 or 48 volts. You don't need to go for a high sophisticated and also costly HV system. And in the A segment, as the demand is very little, a battery electric vehicle might be also very useful in this case. If you're talking about a very, very big SUV, a very heavy vehicle, which can be also more costly, as the customers are able to spend more money on it, we can use high sophisticated diesel engines with a very high efficiency. but for sure also much higher costs. If we want to have a hybrid vehicle, then we most likely need to go for a HV system, as the power demand is much higher and cannot be covered by 12 or 48 volts only. And yeah, for such vehicles, a battery electric vehicle, battery electric powertrain is maybe not the right one, as you would need very big batteries to cover a certain range and so on. One question to you: why is a diesel engine way more expensive than an Otto engine, a gasoline engine? Do you know why? There are some drivers for that, some contributors to the costs.
Diesel engine needs to be more robust, so they require more material. In that way, they are more expensive to build, I guess.
Yeah, that's definitely right. This is definitely one aspect to consider. Yeah, you know, the pressure in the combustion chamber of diesel engines is much higher, and therefore you need to design more robust engines. You will have also more heavy engines to withstand this higher pressure. This is one aspect. What else need to be considered for the diesel engine? Yeah, the pressure of the fuel injection is much higher. Their latest diesel engines have fuel pressures up to way more than 2000 bar. And therefore, you need to have a very sophisticated high pressure system, a very strong, let's say, high pressure pump, very sophisticated injection system, and both are very expensive, as also the tolerances within the production might be only very little to deal with such high pressures. This is another thing to mention. Then for sure, diesel engine must be always turbocharged to deliver the right power density. So therefore you need a charging system, mandatory even, let's say. And last not least, as the emissions of diesel engines are much higher, especially when it comes to particles and nitrogen oxides, there must be a very complicated, a very sophisticated exhaust gas after treatment installed, maybe even with some AdBlue system, which will be also discussed in detail then later. And those things are the main contributors to the higher costs of diesel engine. Okay, then let's move on. So as you for sure know, in the past and maybe even nowadays, there is a very high dominance of internal combustion engine. So means 80, 90, maybe even more than 90% of the vehicles are powered by diesel or gasoline engines. But this one will change. So in order to meet the legislation, as I already said, more and more hybrids are used, and also more and more pure battery electric vehicles are used. And for the future, for the 2030s, for example, we will have a much higher diversification when it comes to the powertrains. For sure, internal combustion engine remains dominant, no doubt, but almost all of them have some hybrid functions already today, but even more in the future. And then the market penetration of battery electric vehicle will become more and more, and there will be no more the one and only solution, but there will be different powertrains used to cover the use cases more specific. So when it comes to small cars, to passenger cars, to be used in the city, in the urban or even in the rural area, there is a high utilization of electric motors expected, but for the heavy vehicles and for the very long distances to cover, as I said, the internal combustion engine for sure will remain very relevant still. But yeah, as I said, the main message of these slides is that the diversification becomes more and more in the future. Okay, now we have been talking a lot about vehicles and powertrain architectures, and the combination of both must withstand, as I said, different ambient conditions worldwide, as well as many different driving cycles, and both of them will be subject of the next few minutes. Yeah, as you can see here, a vehicle must deal with lots of ambient conditions. So mainly it's about the temperature, but maybe also about the moisture, maybe about some dust, about rain and snow, and so on and so on. And the vehicle must be operated regardless the ambient conditions, and this must be considered in the design phase of the powertrain and the vehicle. And in order to be able to test the whole system accordingly, many car makers and also some suppliers have established testing centers, and one of the most powerful, let's say, is the Environmental Test Center of Ford in Cologne in Germany. So as you can also see on the pictures, this one is a test bench to run the vehicle on different speeds, up to 250 kilometers per hour. But you can also adjust the ambient conditions according to your needs. Yeah, you can adjust the ambient temperature of this test bench from -40, which is the lower specification limit of many specification books in the automotive industry, up to plus 55 degrees Celsius, means you can cover all the temperatures that occur worldwide. You can also adjust the relative humidity from 10 to 95%. You can even adjust the air pressure from an elevation level of -100 meter up to 5,200 meter, means you can cover the air pressure of the Death Valley as well as the air pressure of the Mount Everest base camp. And you can also make it snow or rain, and you can turn on the lights to simulate solar radiation up to 112 kilowatts. Question to you at this point of time. So how does the air pressure influence the powertrain? What do you guess? The powertrain and the energy management, therefore. Which system highly depends on the air pressure?
The intake cycle of an IC engine.
Exactly. So the higher the elevation level,
in this example, more than 5,000 meters even, the lower the air pressure gets, and also the density of the air is reduced. And therefore, the oxygen transferred to the internal combustion engine also becomes slower. And this one, and how to overcome with the charging pressure of the turbocharger, can be then also tested in such an environmental test center. By the way, with the lower air density, the cooling also becomes lower, because if then less air mass flows through the radiators, the cooling becomes also lower, the performance of the cooling. Okay, yeah, so much about the environmental, about the ambient conditions, and then the next step is to define the right driving cycle
to apply. Yeah, first of all, you need to consider the ambient conditions, but then it's also about how to operate the vehicle in the test. And for the authorities, it's actually only about efficiency and ecology. Yeah, the driving cycle applied is there to check whether the vehicle meets the requirements in terms of greenhouse gas, carbon dioxide emissions, which is linked to the efficiency of the vehicle, and if the vehicle meets the requirements regarding ecology and therefore the emissions of air pollutants. But this is not the whole story to consider during the design of the vehicle, and this is why the car makers and the suppliers have designed some more driving cycles to also check dynamics, to check comfort, and to check whether the protection is sufficient. We will introduce some more examples for this then later. Yeah, what must be defined can be seen on the table here. Yeah, we have different phases. First of all, in general, you need to define the equipment of the car. Yeah, it's a difference if you check the fuel consumption, the emissions of a very standard vehicle without any extra equipment in it, or if you test a fully equipped car with the biggest wheels, then maybe some special equipment like air conditioning and so on and so on. So this one impacts for sure the demand again of the vehicle. Then in the next step, you need to define how to treat the vehicle before the test. Yeah, the so-called energetic preconditioning. Yeah, it's defined how you prepare the vehicle. Most likely, you need to store the vehicle for 24 hours with a certain temperature to really make sure that the whole vehicle and all the systems, all the fluids and so on have got a stable temperature of, for example, 20 degrees Celsius when it comes to the WLTC. Or if you want to check how the vehicle behaves at very, very low temperature, you need to make sure that the whole vehicle is cooled down to, for example, -7 degrees Celsius, and therefore you need to first store it for a certain amount of time, maybe 24 hours, as I said, under such temperature. Then you also need to define the state of charge of the battery. It's a difference if the battery, the 12-volt battery or the 48-volt battery is fully charged or almost empty. All such things, the preconditioning must be defined and carried out before the test. And during the test, it's then about the velocity profile. It's about the load of the auxiliary consumers and for sure the ambient temperature. Again, it's a difference if during the test the air conditioning is running or not. Yeah, here you can see the velocity profile as well as some boundary conditions for two driving cycles defined by the authorities. The first one is the NEDC, the old one, and the second one is the WLTP driving cycle. And as you can see clearly on the graph, the NEDC is not that sharp, let's say, regarding the velocity profile as the new cycle, the WLTP. It does also not last that long. So in the past it has been 1,180 seconds. Now it's 1,800 seconds. And yeah, then there are also some comments here shown on the slide. So the starting temperature for both are 20 degrees Celsius, which may not cover for sure all the temperatures occurring during the use phase of the vehicle. So if you test at 20 degrees Celsius, the fuel consumption or the consumption of electric energy for the battery electric vehicle is definitely lower than if you run the same test at -7 degrees Celsius, because the whole system needs more time to warm up, and also the heating of the interior requires more energy. Then you can see that the time standing still in the past for the NEDC was much higher, 25%, than now in the WLTP, where it's only 13%. And such aspects may affect the rating of a stop-start system. So if the time standing still becomes less, then also the effect, the positive impact of a stop-start system becomes lower. Next thing to mention is the distance to cover, the length. So in the past, it has been 11 kilometers, now it's 23 kilometers. So what do you think? How does the distance to cover in the mandatory test by the authorities impacts the design of your powertrain? What do you guess?
Sorry, can you repeat the question?
How does the distance to cover during the mandatory test by the authorities impacts the design of your powertrain? So just imagine you need to design a plug-in hybrid powertrain. Why do you need to consider the distance to cover during the tests defined by authorities?
Is it to do with the amount of energy we're going to be needing to put into the vehicle, or electrical current also for the battery to hold to withstand the test?
Yeah, exactly. So if you have a plug-in hybrid, yeah, then for sure your aim is to cover the whole test purely electric. And therefore you need to know what's the actual length of the test, how many kilometers to cover in order to design the battery accordingly. So if the test takes longer, then the battery also must be bigger, at least if you want to cover the whole test purely electric. But it's not only about the energy of the battery, it's also about the power you need to pass the test, right? So again, if the test cycle becomes sharper, if you need to have higher acceleration and maybe also higher maximum speed in the test, then you also need to consider to use a more powerful e-motor in case of a plug-in hybrid. So in the past, for the BMW 1 Series, the maximum power of the NEDC was 34 kilowatts, and now it's 47 kilowatts. So if you then again want to run purely electric with the plug-in hybrid, then the e-motor must be also more powerful than in the past. So it's about two things. It's about the energy of the battery, but it's also about the power of the e-motor then. Okay. By testing in this way, you will receive a certain result in terms of fuel consumption or energy consumption, and then there might be a difference in the real usage of the vehicle. So as I said, if you use the vehicle in a very cold environment or a very hot environment, then you will add some extra energy needed for the heating, ventilation, and air conditioning of the vehicle, for sure, no doubt. And it also depends on how the customer operates the vehicle. So if it's a very sporty driver, then the fuel consumption may even more increase in the real life, let's say. But you can also lower the actual consumption below the value of the test. So this is a very, very high influence of the actual customer later on operating the vehicle. As you can imagine, so if the ambient conditions are very severe, sorry, not severe, if the ambient conditions are very not very severe, just 20 degrees Celsius, not very hot and not very cold, and if the maximum and the average power needed to pass such tests is very little, then this one can be for sure not used to check whether the vehicle withstands all the different usage later on by customer. And this is why car makers and suppliers have defined many more tests in order to check the powertrain in the vehicle in the design phase. And for this, you can distinguish between three different levels, if you like. The lowest level is the component testing. So, for example, you can define a very sharp testing procedure for a turbocharger. So, must be very sharp, must be always sharper than the conditions or the usage that can occur later on, in order to be on the safe side, in order to be sure that if the component passes the test in the design phase, it will then also not fail later on in the mass production and the usage by customer. So this is the lowest level, the component testing. As I said, for example, testing of a turbocharger. Then you can, in the next step, test a system. System could be, for example, an internal combustion engine. And in the last step, you for sure also test the whole vehicle. So components and systems are tested on a test rig, on a test bench, and the vehicle can be tested in different ways. There are many tests where the vehicle is even standing still in the climate chamber to check the warm-up of the interior, for example. Then you can put the vehicle on a dynamometer or a wind tunnel. You can put it or drive it on a test track, or last not least on public roads. And then it's as I said, always about checking whether the protection of the components, systems, engines, and vehicles is sufficient and there are different examples, different focus for this. So, for example, there could occur a high stress due to a high load. Yeah, so, for example, you can check your engine for 1,000 hours running on maximum power on the test rig. Then you can, for example, check whether the cooling is sufficient, whether the turbocharger can withstand a high mass flow and a high temperature of the exhaust gas, and so on. But for sure, you cannot check the endurance of all the components. So do you have an example for a component which cannot be checked by running 1,000 hours on maximum power? So which component of the engine, of the powertrain, will be not challenged by such a test? What do you guess? So this one is definitely valid to validate the turbocharger, as I said, but which component may be not challenged by this? Running 1,000 hours on maximum power. Can you still hear me?
Yes, we can.
Great.
Yeah, is it the one with the stress due to high load under normal conditions?
Yeah, as I said, such a test will be very useful to validate the turbocharger or something like this. But for sure, such a test cannot be used to validate the starter, for example, because in such tests you use the starter just one time to start, and then you will not use anymore. It's the same, for example, with the throttle. So in this test, you cannot check whether the throttle withstands the real life later on, because it's always in the same position. It's always on full throttle, but you don't change the position. And this is the same with valves, for example, with the wastegate of the turbocharger, which may be not used or at least not change its position, and so on and so on. And this is why there is a second focus to check vehicles to check components which are stressed by a high recurrence. So, for example, again, to check whether the start-stop system is okay, whether the starter is okay, you can, for example, start the engine 500,000 times, and then you will see if the design of the starter is valid or not. And last not least, you can also focus on customer-oriented usage. For example, you can drive the vehicle on the road for 200,000 kilometers. These are the different focuses: stress due to high load, stress due to high recurrence, or customer-oriented usage. Okay, yeah, as promised, I will also introduce some examples for extreme scenarios for driving cycles. 4 of them shown on slide 43. The first one is cold start. Target functions to check are efficiency, ecology, and comfort. For efficiency, it's about checking how quick the engine can warm up to have a good efficiency to lower fuel consumption. When it comes to the ecology, it's about the warm up of the exhaust system, of the exhaust after treatment. It's about checking how quick the three-way catalyst, for example, converts all the air pollutants, and for sure it's also about the comfort, checking how quick the interior warms up. And one test for this could be starting with -7 degrees Celsius. The vehicle is put in a climate chamber, and you then just start the engine. Speed is 0 km/h, means standing still, and you are then idling. The vehicle is just idling, and then you can check, for example, how long it takes till the interior warms up. Then there are some examples to check for dynamics and protection. Very popular one is the slow Escant. This one is performed at a temperature of 40 degrees Celsius, very little speed, for example, 30 km/h, and maximum load and minimum speed of the engine. Yeah, you can imagine in the summertime going up a very steep hill. This one for sure can be used to check whether the protection, whether the cooling is sufficient, and whether the vehicle is able to deliver the right power, the right dynamics. Then another one is testing at maximum speed at ambient temperature, for example, of 20 degrees Celsius, and which load and which speed of the engine then occurs depends on the car. So there are some vehicles with a speed limit, 250 km/h, for example, but anyway, a very powerful engine, for example, BMW M5. And then the load and the speed at 250 km/h maybe not maximum, but it's different for another engine. At the same speed, a less powerful engine may run then on full power already. Yeah, and last not least, racetrack test, also used at, for example, 30 degrees Celsius, very volatile speed, and therefore always volatile operation of the engine as well, and most likely many times maximum load and maximum speed of the engine. Okay. Yeah. As I already said, shown on slide 40, by the way, the customer, the driver of the vehicle, has got a very, very high influence on the fuel consumption, and in order to decrease the influence, in order to therefore decrease also the fuel consumption, autonomous driving could be used. So, for example, there has been a research project of Porsche called ACC InnoDrive, and Porsche checked out how autonomous driving could reduce the consumption, and the system, as shown in the graph below, always chooses the most efficient velocity to take and adjust then accordingly. Yeah, for sure, the maximum speed is defined by the speed limit, but is maybe also defined by the road itself, if it's very curvy or not, and so on and so on. And also the minimum speed should be given. So maybe you remember some minutes ago we discussed that even with very little speed, the fuel consumption may rise because the influence of the auxiliaries becomes bigger. And between these two values, the maximum and the minimum speed, the ACC InnoDrive always chooses the right speed in terms of efficiency. And at that time, Porsche said that this can lead to minus 10% fuel consumption. Another thing, how predictive energy management can positively influence the energy, also the fuel consumption. as well is shown here on this slide. Yeah, you can see basically two strategies. Yeah, that the first one is the red one, and then there are two blue lines. And the red line shows the state of charge of the battery of a plug-in hybrid without any predictive energy management. Yeah, and as you can see, the state of charge is always on almost the same level. Now, question to you. So, if you know the route to take, so if you know what will happen in 5, 10, 15, 20 minutes, how can you better adjust the state of charge, the working point of the battery of a plug-in hybrid? So, what would you do if you know whether there is a city to come, or a highway, or the next city, and so on? How would you adjust the state of charge of your battery?
So can you say the question again?
So yeah, once again, the red curve shows the state of charge of the battery of a plug-in hybrid without any knowledge about the route to come. This is the red one. You can see it's almost always on the same level. And the blue curves then represent a
Number one, could you please
different
sing the opening
strategy.
to I Want It
Yeah?
That Way?
Means the
Okay.
discharging and the charging of the battery by knowing the route to come.
Number two,
Yeah?
keep it going.
And the question now to you is, how would you adjust
three,
the energy management of the battery of the plug-in hybrid
Number
if you
four,
know what will be next? If there will be a city, or if there will be a highway, if there will be a mountain, or whatever. So how could you make use out of this information?
Now number five, I never wanna hear you say, I want it that way.
Probably would minimize the amount of energy being burned during the city drive, where it would be generally at one level of steepness, that would be going up and down, and you'd probably you'd probably maximize the amount of power, and not only power, how much charge you have coming up to the times of either going on a freeway or driving into a mountain or something, changing the like a rise in the road surfaces, also going up hills.
Yeah, very good. So this one can be also seen in the graph, right? So if the system knows that after a certain distance, the vehicle will leave the city and will drive on a highway, the system can discharge the battery as it's shown here. You can drive purely electric in the city. You can reduce the state of charge of your system, because then on the highway you may anyway need the internal combustion engine. And then after leaving the city, you can turn on the internal combustion engine, you can run the vehicle, and you can also charge the battery again. You can charge to a maximum amount, which allows you to pass the next city, city 2, shown here, again pure electric, to not have local emissions there, to also have no noise there. This could be one advantage of such a route-based operating strategy. Yeah? What would be another example? So if you know about what is about to come, how could you better manage your powertrain, your vehicle?
would it just be more along the lines of planning out your route and maybe even having an integrated navigation system was connected to the vehicle to let the vehicle know as well that it's going to be changing, or for it to switch over, like turn on the internal combustion engine when it reaches like a certain speed for a certain period of time and enter like charging.
Yeah, exactly. Another example could be if you drive on a mountain with your hybrid electric vehicle, then it's definitely a good idea to discharge the battery when going uphill, right? When going uphill, you can use then the electrical energy to support the internal combustion engine to lower therefore consumption, and you can then ensure that on the top of the hill the battery is empty, because when you drive downhill again, the battery must be empty to recover the elevation energy. So if you're going then downhill again, you will brake a lot. And if the battery is empty, you can use the e-motor, you can charge the battery again. If this is not the case, you can also not recover the elevation energy. And this would be another advantage of such a route-based operating strategy. Okay, but what else needs to be mentioned here? If you go for such things, yeah, especially for autonomous driving, yeah, you need a high amount of sensors, and you also need control units to process all the data gained and to run the vehicle accordingly. And these systems, especially the control units, they also need a lot of electrical power, sometimes more than 2 kilowatts. These computing platforms are even liquid cooled, and this then increases the power demand of the vehicle. So this is exactly what was shown here in the beginning on slide number 13. This may increase the energy demand, especially on low speeds, significantly. So if you consider, and also go to this slide again, just 1 second, sorry. Coming back to the driving cycles. So if you consider that in the NEDC driving cycle, the mean power was 4 kilowatts, and then you add another 2 kilowatts just for the computing of the autonomous driving, you have 1.5 times the power needed. So this one must be considered. There are some positive impacts for sure of autonomous driving, of predictive energy management, and so on. But you always need to consider the energy used to run such system then. Okay, yeah. Then let's already go to the core of the lecture, to the energy management in terms of demand, supply, and recovery. And for the demand, I would like to highlight heating, ventilation, and air conditioning systems. Such systems have actually different tasks to take care of. For sure, it's about heating and cooling. I think that's quite clear, but it's also about dehumidification and exchange of air. And the goal is to ensure comfortable temperatures, the right air moisture for sure, and no smell, minimized portion of carbon dioxide in the interior of the vehicle to make it comfortable for the passengers then. In addition, such system can be also considered as contributors to the so-called active safety, as the concentration and so on of the driver for sure is much better if the temperature is comfortable, if the moisture is comfortable, and there have been some studies, by the way, which showed that a temperature rise from 25 to 35 degrees Celsius equals approximately 0.5 per ml blood alcohol concentration. And I think everybody can imagine, yeah, if it's very, very hot in the vehicle, then for sure you are not performing that good as driver as it would be the case with the right temperature. Yeah. Now I would like again to ask a question to the audience. The HV system, the power needed for cooling and heating of a vehicle is very, very high in comparison to a house, for example. Yeah? What do you guess? Why is that? What is the reason for that? Why do you need, for example, 5 kilowatts power to cool down the interior of a vehicle? What are the main contributors for such high power demand of the HVAC system of a vehicle?
So I think because the material of the vehicle is lighter than building, it cannot retain the heat cannot be retained. So if you need arts, for instance, and the body of the car is slimmer than that of the wall of your house, so you need to keep on heating the car to maintain that temperature compared to your building.
Mm-hmm. Okay. What else?
Is the factor of movement with the air going across the vehicle a factor as well, as in it will take away majority of whatever temperatures or air pressures are going on inside the vehicle. So it has to be like consistent of maintaining the humidity and the temperature as a result of just the air going across it, kind of thing, trying to dispel all the heat.
Okay, something else?
So also the cooling system is used to cool the batteries. So it needs to also cool the interior and also the batteries.
Mm-hmm. Yeah, that's right. And this one will be discussed then later in the according chapter. Yeah, let's quickly talk about the power demand caused by the vehicle interior. So the volume actually is very little, maybe 3 cubic meters or something. But the thing is that you have at least if all the seats are covered, many persons in such a low volume. So, for example, when it comes to an office building or something, you have 10 cubic meters per person. In a vehicle, it's just 0.6 cubic meters per person. Means the density of people in the space in the volume is very, very high. Then the mode of operation is most likely instationary. Yeah? You need a lot of power to heat up or cool down from very low or very high temperatures in a short time, which is different with the office, right? So if you park your vehicle outside in the winter, in the night it will cool down to minus 10 degrees Celsius, and then you need a lots of power to heat up quickly, and this is not the case for the office. So the office just does not cool down in the night to minus 10 degrees Celsius, and then needs to be heated up very quick afterwards. So this is another difference. Then you have actually no protection against direct solar radiation. So in the office, yeah, you can use some blinds or whatever. It's different in the vehicle. So therefore, the heating up of the materials inside the vehicle is very, very high, can go up to 100 degrees Celsius, which is different in the office for sure. And then last not least, you need a very high air exchange rate because of that many people occupying a very little volume, and all these things lead to a very, very high power demand in comparison with stationary applications such as the office. Yeah, let's quickly check how the system works, how the air flows inside the vehicle. Yeah. First, it passes an air filter. Then there is the blower, yeah, to suck the air from the outside and to blow it into the interior later on. And then you have two heat exchangers. You have one heat exchanger for cooling. This is the so-called evaporator of the air conditioning system. We will discuss now. And there is a second heat exchanger for the heating. And this device here, the heat exchanger for heating, this one is the heat exchanger for the recovery of the energy in the hot coolant. Yeah, we just talked about it today, that you can use the hot coolant of the engine to indirectly heat the interior. Means you pass on the air from the outside on a heat exchanger. The air is then heated by the hot coolant and afterwards released to the interior. And this is also considered as kind of recovery, because otherwise this energy would be lost. Okay, we can skip page 51 and also page 52. We can also skip this and then move on to the major principles of air conditioning systems. And this is now also the time again for me to ask you. So, do you know how air conditioning system works? So, how can you cool down the air, let's say, to 8 degrees Celsius from starting with 40 degrees Celsius? Does anybody know how air conditioning works? Are you still there?
Yes, we are, sir.
Okay, great. Does anybody know how air conditioning system works? Or maybe another question in the beginning. So when do you need air conditioning actually?
When
do you
it's
need it?
when the temperature is pretty higher, let's say 23 to 30 degrees, and you need to cool yourself down. You need that then.
Mm-hmm. Yeah, but generally speaking, what do you think? When do you need air conditioning?
In the summertime.
Yeah, okay. You need air conditioning system if you want to cool down the interior or the battery or whatever on a temperature below the ambience, right? Below the ambient temperature, then you need it. So if you want to have a temperature of 20 degrees Celsius in the interior, and outside there are 30 or 40 degrees Celsius, this will not work. Then you need an air conditioning system. When you want to go below the temperature of the environment, okay? And how does it now work? How can you achieve a temperature below the temperature of the environment?
By removing the heat from the area which needs to be cooled down.
Yeah, okay. And how does this work in particular? How does this work?
Coolant. Yeah.
Okay, so I will explain. Just imagine you would like to cool down the plate of the table, the top of the table in your room to 8 degrees Celsius. So let's consider in the room we've got, let's say 30 degrees Celsius, and we want to cool down the table to 8 degrees Celsius. How can this work? The major idea is to use a fluid, to use a special liquid which evaporize at 8 degrees Celsius. Yeah, in your room there is one bar and 30 degrees Celsius. Also the table has got 30 degrees Celsius, and then you take a fluid which evaporates at a temperature of 8 degrees Celsius and one bar, and you put one drop on the table. What happens?
Most likely evaporate.
Exactly. So the drop you put on the table immediately evaporates because the temperature of the table, 30 degrees Celsius, is above the evaporation temperature of this liquid. Okay. What happens to the table?
The heat is being absorbed from the table by the drop.
Exactly. And what happens to the temperature of the table?
It reduces.
Okay, but to which amount? To which value?
To 30 minus 8. That's 22.
No. So the table,
the energy required, the energy required by the absorbed by the droplet will be proportional to the decrease in temperature.
Yeah. So as it's just one drop, that the temperature will maybe not decrease significantly, but let's say to 29.9 degrees Celsius. Okay. How should we proceed? So if
you want to reach 8 degrees Celsius, how should we proceed?
We need a flow of that liquid on the table.
Exactly. So we add another drop, and the temperature goes down to 29.8 degrees Celsius. And we add another drop, and it goes down to 29.7 degrees Celsius, and so on and so on. So if we then apply a continuous flow of the liquid, then there will be also continuous evaporation, and the temperature of the table reaches maybe not 8 degrees Celsius, because there must be always a remaining difference in the temperature to ensure the heat transfer from the table to the liquid. But you may reach, for example, 8.5 degrees Celsius or something. So if you apply continuous flow of this liquid, then you will in the end finally reach the desired temperature. Okay, how should we proceed now? So I think leave it like this is no good idea, because then you always need to refill this liquid, right? Because this liquid is then vaporized.
We'll use a compressor to compress the liquid, and then it will be converted to...
Not the liquid.
Sorry, the vapor.
Okay.
We'll compress the vapor and bring it back to the liquid form and use it again.
No, not to the liquid form. This may not work. So
in heat exchangers, passing the liquid to a cold metal.
It's no liquid anymore, right? It's the vapor.
So we just keep it a vapor format throughout, instead of having a liquid, we have a coolant vapor.
So I think the main goal was already achieved, right? To cool down the table. So which is just an example, could be also the interior. Yeah. This one is already accomplished. How should we proceed now? So if you don't want to refill the liquid all the time, how should we proceed with the vapor? What happens in the next step to the vapor?
You need to recycle the fluid with a closed cycle. Basically, I think that the liquid now is vapor, you have to condensate back to liquid. When you're working on the fluid cycle, you're working with a cycle on the fluid, because you have to restore its original status, to going back to maybe, lower the temperature of another table, I don't know, something like that.
Exactly. And how do you do this? I will explain, and then we go for the next break. So the next step is then to suck the cold vapor by the compressor, right? So the vapor also has got 8 degrees Celsius, and then we suck this cold vapor by the compressor, and we compress it to a high pressure. And what happens then as well? So if you go for a high pressure, if you compress it,
the temperature drops?
No, it rises. The temperature becomes higher, right? If you compress it. So you take the cold vapor, you compress it to a very high pressure until the temperature is also high. And the temperature after the compression must be way higher than the ambient temperature. So in our example, we should compress the vapor to a pressure to reach, let's say, 100 or 130 degrees Celsius, something like that. Then you have hot vapor. What happens next? What happens next with your hot vapor?
That heat is released into other environment.
There's lots of background noise. I didn't really understand.
The heat needs to be dissipated into another environment, a colder environment.
Yes, that's right. Yeah. So then so the environment has still got 30 degrees Celsius. I think this is already agreed. Yeah. But then you have the hot vapor, and the hot vapor with, let's say, 130 degrees Celsius or something like that. Yeah. This one can be again cooled by environment with 30 degrees Celsius. So then you send the hot vapor into a heat exchanger, the so-called condenser, and you cool it down by the 30 degrees Celsius environment. You cool it down till it's again liquid. Yeah. Then you reach the state 5 here, shown in the diagram. And what is then still needed to make the cycle close? To have again a liquid which evaporates at 8 degrees Celsius. Sorry.
You need to expand the vapor.
Exactly. It's no vapor. It's
So
maybe even liquid.
Yeah.
Exactly, because
Like
liquid is then
atomization?
like what?
Like atomization. The single drop must be atomic, like.
No. So, as you can see in the diagram, the vapor has been cooled down to 30 degrees Celsius, but it's still liquid in the end because of the still high pressure. So it's still under pressure. And if you then want to again have a liquid or a fluid which evaporates at 8 degrees Celsius, you need to release the pressure. You just use a valve to go down to the pressure of 1 bar, for example, again, and then the cycle is closed. Then you have again a fluid which evaporates at 8 degrees Celsius, takes the heat of the system to be cooled, for example, the battery or whatever, or the interior, evaporates, then the cold vapor is sent to the compressor. It's compressed till the temperature is high enough to be again cooled by 30 degree environment. So this is how the AC system generally works. Actually, very, very simple approach. Okay, and now we will go for a break for 30 minutes, and then we will come back and perform some calculations on that. Okay. So let's meet again. Let me quickly check. Let's meet again at let's say 4 p.m. 4 p.m. your time. We can meet again. Okay.
Okay.
Sounds good.
See you later. Bye bye.
Bye bye.
Take it.
Connected. Disconnected. Disconnected. User entered your channel. Disconnected.
Transmitting from the future. Come in Paris, Amsterdam, London, Houston, Atlanta, Chicago. Come in Cape Town, Kinshasa, Nairobi. You are tuned into FM broadcast, celebrating Black futures in sport and culture.
Yo. Oh yeah, so one sec. Oh yeah, you're in. Let's go. Love the profile picture, Axis. More difference is too high. I guess Axis maybe because he's unranked, because we could play with Unica.
I'm probably too low.
Yeah. Or who?
Me.
Maybe. No. It's Axis.
Hello. Yeah, might be me. I'm on my Smith. I'm unranked on it, like fully unranked. So.
Oh. So I wasn't too shit. Damn.
Wait. What's your MMR? 3399. But you still can't queue with me in the lobby. I swear you hard reset.
The highest one is maybe grow. Yeah, 3399.
Give me 2 seconds. What is this?
No, it's me. Yeah, it's actually.
Wait, no, I can queue. My MMR is 2350, which means.
But when Mari left, we still couldn't queue.
Wait, try queue.
Oh no, yours is like 40 too low.
Ooh,
oh, I thought yours said. Yeah. I thought yours said 39, not 99. Okay, yeah, give me 2 seconds.
I'm gonna go get a drink while Axis sorts that out.
Apologies,
yeah.
I'll be there.
No.
Memento. I played 4 games yesterday, and 3 of them were against cheaters.
Well.
So my Smurf stats have taken a hit.
I get an alpha. Let's go.
Yeah, I'm loading up now, mate.
Does Unica not want to go in a VC?
Others know, bro. Why Laces come?
Does Unica win access? Or Mari, sorry?
I didn't. Yeah.
Does Unica not want to go into a VC?
I don't know.
My game is.
I'm running access.
Yeah. I'm waiting for my Ubisoft Connect to load. There you go.
Let's go.
I should just be joining now. I started yesterday like one game off
Oh,
diamond, and
amazing.
now I'm mid plat 2, just because
Yeah.
of cheaters. So I'm owed a solid like 400 elo.
Yeah, I don't think I got rollback at all the whole game or the whole season.
I got
Me
one bit
neither.
of rollback.
We face a lot of cheaters because of me, and we didn't get any back.
Yeah. Of course. Definitely can help him. No, do.
Wait, it's mute is banned.
Yikes! Can I talk?
Ew.
I can't play SMG
Weird.
11. I'm sad.
Oh, do you want to play Smoke?
No, as well.
Yeah. Alright, it's finally happening. America, it's finally happening. I'm gonna get kills this game.
Don't know about that.
Okay. GG, Mental's already down in the dumps, F.
Mental's already done.
Yep.
Stack disbanded.
Yep. That's a stack disbander. And this guy doesn't load. Por favor.
Well, it's called Pluto.
Fucking Pluto. Oh, yeah. Oh, what is that? Bugged rotates. Weird, man. Feels weird, man.
That's why I was making a running rotate next to that. That was a hole. So we get a long angle.
Oh no. Yeah. Oh. Well, I missed my electric claw.
Someone can go blue here. I need to make.
Yeah, I'm on blue side. I'm getting the library hatch too, so they don't just jump in.
Make some holes here, please. Or here.
Just want to hold here if he comes up the ladder.
Picking me from lobby, picking me from lobby. Outside
Library
lobby.
window? Or maybe below, bro.
Hello. You leaving now? You reckon
Injure
you
or
reckon he'll be
prone?
back at
Maybe
full?
nading you from K9, bro.
Yeah.
No.
Yeah, he's probably below. I go below.
I wasn't told the gap I had before it happened. You just said to me, yeah, we're gonna take a break now. If I could have pre-planned the break, I would have told you about it. Okay. Okay.
Big window repel.
You driving back now?
K9 door.
Yeah, I'm just playing it while I'm on this break.
I'm going above again, bro.
I love you so much. I'll see you soon. I'm really excited to see you. Love you. Bye bye.
Dead K9.
Nice.
My game's just typed me out while I'm in the middle of a door. Did I die?
What's this sound?
No.
How did I not?
Last one, bathroom balcony last. Heard?
Yeah, it's this. Huh? I didn't know they make a sound. Actually, bathroom block?
It's not on there anymore. Oh, he's on the roof.
Yeah, he is. Yeah, he is. Or roof, okay.
Yeah, he's just on the fucking
Good
roof.
night.
Freak, man.
What a weirdo. ¿Qué degenerado, tío? All the way on the roof or what?
Yeah.
Yeah, top of the roof, mate.
So weird. That's the angle. Oh, this one, yeah. Pretty busted.
I'm gonna go out. Pongo los huevos.
Okay, I'm coming with you, bro.
There is no, there is
Okay.
no.
K9.
Yeah, nasty angel. Let's go. First round, first dub. They're gonna start rolling it, and they're 4v5, so GG. Maybe it's a bar round actually.
Vaticano cancel.
Yeah, go, but I don't know why we went bottom. But
Yeah,
shit.
bar's much better.
Secure the area. Keep the bombs protected.
Wait, I'm gonna close this because of the mirror. You wanna... Can somebody get the stockpile? I don't have time. Or potentially I do actually. Yeah, never mind.
Who the fuck reinforced that wall from that side?
Oh, that's unlucky.
Oh.
That's fine, just blame Unica and move on. Wait, mute spam. Ooh.
K9, someone play Mass.
Play where?
Mezzanine.
Oh, mezzanine, okay. I'll give you a shield, that's a normal shield. Do we have all the shields upstairs? Oh yeah.
Yeah, I put both down.
Okay, so I guess I'll put one in sight.
We got no one inside at the moment.
I'm here. Oh.
I trade. Oh my lord.
Okay, I'm out.
Main door low.
They're droning the top floor.
Evaluation, okej. Jag så galen då. Main window, main stairs window, yeah. Rotating around. He's leaving. Take care with mud. Muddy, can you hold mud?
What's on library window? Library window.
Yeah, coming up mixer from basement.
Okay, bro. I'm holding you.
Take care blue stairs as well. Coming up.
Bottom blue stairs. Floor is dead.
That's the below guy or not?
That was bottom blue stairs.
Okay.
Yeah.
Floors? Okay, yeah, he's dead.
Outside games window, maybe?
No. Yeah, in games. He dropped from the hatch or what? The window was closed. Yeah, he dropped from the hatch.
Oh, it sounded like he was down or some shit.
This hatch, this sound was so scary. Like I had no idea.
I
what
was
it
stood right next to him. There's no way he jumped
Yeah.
in from above.
Really?
Yeah, there's no way. I was stood.
So
in
he
the
walked
library.
in from blue stairs or something. He was sitting right in front of the window, but the window's closed. Where? Fucking dining, like crouch walking, short, like 5 seconds left of the round.
Imagine.
Where did the thermite come from? Now I need to check the match replay. Like I have no idea what happened.
I think he maybe was being.
I don't know.
He's a ghost.
He's a ghost, yeah.
No, I'm good. Do you want anything?
So when the camp gets destroyed, he then spot thermite.
No, do you want anything?
No, he never came. He never came in. I was in bar the whole time, and he died in games, like on the window, but the window was closed.
I mean, but he can't be coming up from
Hello?
boosters
I'm
as well
talking to you.
because the Goyo, I mean, Mari was watching.
Hello?
that,
Do you
was
need
checking
it?
that.
Are you getting anything?
And Access said he had above as well. So
No.
I don't know. I guess he's a ghost. Maybe I mean one explanation
I'll send you
that
a
could
text, okay?
potentially have happened is that he opened the window and jumped in, and the window was bugged, like it looked like it was closed.
Yeah.
But apart from that, I have no fucking clue. I actually have no
Super
idea. He phase shifted into the side or something.
No operator.
Yeah.
Can just materialize
Who's
through walls.
this? Oh, it's Ellis. Oh, okay. Okay, dude. I play mute way more than I play smoke. So every time I play smoke, I walk up to a reinforcement and put a gas canister on the reinforcement.
Oh no, I do the opposite. I throw a C4 on the floor, thinking it's a shield.
Oh yeah, I've done this in the past as well, but recently I've been playing way more mute, so
I just do both. So stupid.
I don't have this. We don't have any. Okay.
We have no bridge now.
Also, for some reason in this scrim, I was playing Goya with TCSG. I thought I was smoke for some reason, and I threw a
Dear.
C4 on the floor then as well.
Oh dear. I have I don't know why, but my mute button, like my mute microphone button, on TS, somehow it got bound as my C4 button or like my secondary gadget button. But I never bound it. It's just I don't know, like bugged or something. So yeah, once or twice I've accidentally blown myself up trying to unmute in TS.
outside of
Big
Mainstairs
garage.
window. Yeah, droning outside into fireplace.
Okay, I'm looking for it. I don't see it.
They've jumped in.
I got it.
They've jumped in the window. Not exactly on that ping.
Oh really? There's another drone? I got one in lobby.
No, not the drone, a person.
Oh, a person, okay. Well,
I think you jumped down. If not, then I'm hearing shit. Oh, they might have jumped off the balcony.
They're pushing trench.
is his windows open?
They're pushing trench or not?
Ying, where? Where?
I
What?
don't know. I didn't hear a ying.
Go inside.
No, right? No, it's online. What is he yinging for?
Oh my fucking god. Okay, trench door.
Yeah.
Flores.
No. Luego voy a lo de la Yaye y me avisa. Luego voy a lo de la Yaye y me avisa. Ah, bueno, pues me avisas cuando venga.
Is the gate up? Yeah.
Oh, top blue stairs Ying.
But what, so he just can't delete library or what?
I think so.
Okay, weird.
Okay, email mezzanine. Got both accounts.
I'm on blue stairs.
Still one trench.
Tom main.
I have blue. Not main stairs. There's 2 mirrors for main stairs. Did he walk down main? Anybody watching the cam or not?
The main cam's gone.
Yep. It is. Because the guys are there. This guy's so fucking dumb. Both. Crossed.
Bro, how do you see that? I only saw one guy.
Oh, sorry, bro. I shouldn't die here, and we kind of threw by running at this guy in lobby for no
I
reason,
only
but
saw one guy.
whatever.
Did you see both of them when I peeked there? Because I was fully blind. Like, I didn't see fucking anything.
Let's get this bread, gamers.
Third basement.
Yeah. Dude, that is so weird. How can a drone destroy a giant wood barrel with metal reinforcements on it? And it gets my drone spotted because of course like a giant barrel breaking.
How do these drones go upstairs?
True. Immersion broken. Never playing Siege again.
Yeah.
Plot hole found. Do I have hardware?
Hole found. They're not like Claptrap. Uninstalling right now.
Shout out to Claptrap.
The car garage is clear. Close to the door is clear. Behind the fridge is clear. They have a mirror window up on the west main wall. I can put some help on the charges on it in a sec.
Yeah, there's no denial on the other side either.
Okay, I'll put a cam west main.
Mari, don't open this one because then you can't push the hallway. Just put the X-Kairos and then come to the trench wall as well.
Yeah.
And I don't have a hard breach. If I did, I could get it, but Bandit's on the pillar. I can. All right, nice, yeah. Oh, Eunuch is here too. I thought he was on the main wall. Axe is too saucy.
Wait, I had no fucking nade icon. I literally couldn't let go of my nade. This game's so bad. There's one in coat. Oh, this fucking game is so terrible. I throw the grenade.
I'm with you, Mari.
Pillar, Bandit.
Dead. Bandit dead. Blue looks good. I'm walking in.
No, one taking our back. Mira.
Dude, plan. Just plan here. Again, you. Didn't plan to plan. Yeah, he's on Discord. And I don't know voice chat. Mirror dead. Vigil blue. Where was last girl? He's in connector. What the fuck?
He's not last.
Yeah, why is this guy not planting? I don't know who he is, but he's a.
Oh my god, I was running like a fucking cervatete.
Bro.
Blue and connector. Left side here. Nice shot. My bad.
I should have been aiming in there.
No, because I said last, because where did you die from, girl? Or who did you die from?
I mean, Mira killed me.
Oh, okay. Oh, okay,
I got off the drone and
I thought, yeah, I know.
A nade, and I just couldn't.
So I killed the Mira, and at this point, I thought there was one blue and one upstairs. The guy who killed you. So that's why I just pushed him this way.
No, because as soon as I call Mira Kevin back to blue, you know.
Yeah, I missed this because I was trying to get Eunuch to plan, but yeah, this guy it's a little bit unfortunate to have a guy playing hard bridge every round and not be in Discord.
Bro, I literally couldn't let go of my nade.
I was just,
but there was no icon either. I just couldn't let go.
I hate it because it looked like this guy. No, he's sick. His voice doesn't.
Oh.
That tasty nade, bro.
Access is muted, so.
This game's so fucking bad. Wait, what?
For
Wait, you
like
didn't
2
hear
rounds.
Me? You didn't
yeah,
hear
for
me
like
that
2 rounds, bro.
Time? Bro.
Yeah, bro.
No.
I saw you were muted and I was like, am I gonna say something or no? And I was like, oh,
Bro,
I guess I'll notice.
I got off a drone, started clicking a nade, and then I had no indicator on my screen, and I couldn't let go of it.
Yep. Yeah, that happens sometimes. Sometimes you just don't get an indicator on when it's gonna explode, and that's all. Unlucky.
I couldn't let go of it.
Oh really?
It was stuck in my hand.
That's new. Yeah, that's very unfortunate. I don't think that's happened to me before, but.
Fucking terrible game, right?
If I had voice chat, I would call to Eunuch more, but I don't know. My voice chat's been bugged since the other season, so I can't. Yeah, me too. So.
Yeah, my voice chat was bugged for like 4 seasons on my main account. I could never talk him.
Oh, okay.
Was it?
Yeah, there was someone peeking Solarium.
Okay.
It was all my.
Okay, somebody's watching Big One now.
Lamai isn't holding the window anymore, by the way, so you can't take the fuse.
There's no barbed wire on Astro's does. And Astro's clear at the moment.
Yeah, we don't have diffuser, watch out here. Oh, yeah, sorry, bro. I should kill this guy. I just didn't think he would walk in like that.
Yeah, bro. Don't worry. I mean...
No, it's my bad, bro.
I have a flank drone, can you hold it?
Doesn't give a fuck that his wide swing me. I'm so bad, man, like...
There's one in bathroom. Oh, pfft.
Clapped.
I don't know. I've just died to literally thin air.
I'm dying to being a bot. Seems like a good strat to maybe not be a bot anymore. I'm gonna try.
Yeah, I died to sprinting. That seems like I shouldn't do that anymore.
Could happen.
Yeah, just always pre-fire that spawn peak. It's normally a freebie.
Yeah, I always forget about it. So like that's the only spawn peak I always forget about. Is the reason I go that way is because I remember the other spawn peak from Trophy.
Yeah. Was it just the Solarian one?
Yeah.
Yeah, Solarian window on the boost spot.
Yeah, that's pretty rare. I mean, yeah, not a lot of people spawn pick here because it's it's very risky. Like it's very easy to die to this rock. Right, but if the guy's taking care, he can kill you from behind the trees and you never see him. I mean, the trees on this map are real annoying. Even on the old one, like the trees are so shit because they create so many one-way angles, or not even one-way angles, but like you know where to pre-fire as a defender, and it doesn't matter that there's a tree there, you know.
Still tilted off that fucking nade, man. Ugh.
It's below, right?
Just run flashbangs forehead.
You wanna come to the bridge with me, girl?
Yep. We go see you, bro.
Yeah, they're holding top floor.
That's how to do.
They got no setup
I'm
library
gonna
side or
go.
anything.
Yeah, I'll come library side then.
They have Elysian and Thunderbird.
Oh, what the fuck? I pressed 3? How is 3? My nade button's on my mouse, dude. Like, what's the point of rebinding the key when it doesn't fucking do anything?
I don't know.
Sheesh. It's not basement, girl. I'm not going there. Side's kitchen. Library's
I have
clear.
a join West Main, by the way. They fully reinforced off Trophy.
Box is clear. Top, like heaven is clear. And up to piano, I'm going in.
They didn't reinforce trophy off.
Oh, they reinforced it to fucking the other part. Like Solarium stairs.
Okay, my nade didn't kill me this time. Thank you.
Yeah, I'm coming with you, girl.
He's so lit. No, one main, dude.
Where? Stairs or what?
Yeah, stairs.
Up?
Point down.
Okay. He's gonna come west, man. Last is gonna come west, man.
You got cams now? I'm calling phones.
Planting. Half. 75. I have no more nades because I accidentally dropped one at spawn. Saving KD in basement or what? Ready to rotate up when we didn't notice. He's in bar. Okay. Unica shot me at the same time as the Wamai started shooting, so I thought he was looking at me.
Unica's an imposter.
True.
Can you hear me again?
Yes.
That was rude.
Okay, great. Yeah, then let's continue. I think the major principles of the vapor compression refrigeration system.
This is uniform from here.
VCRS are now clear. And yeah, let's continue. Let's check how to now calculate such cycles. I will guide through this one by one. Don't worry. And you should really pay attention as this is also of high relevance for the exam later on. But again, let's do it one by one. On the right hand side, you can see a so-called pressure enthalpy plot for the fluid used. So the fluid which absorbs the heat by evaporating and is later on then compressed, condensed again, and so on. So the state number 1 shown here is the starting point, let's say. This is where the evaporation starts, moving from state 1 to state 2, from the two-phase region to the let's say, to state number 2, and then the compression follows. The fluid compressed from state 2 to state 3 to reach a very high temperature to be then again cooled by the
you know how I felt the whole time we played with this girl?
degrees Celsius or something like that. This is then the step from state 3 to 4, the condensation, and afterwards the step from state 4 to state number 1 is the expansion. So this is the cycle we've just
I think
talked about.
Oh fuck! I forgot to do the thing, bro.
As I said, now it's about the calculation of such cycles, and in order to do so, you actually need to know about the first law of thermodynamics for heat exchangers and for the compressor. Yeah, the first law of thermodynamics for the heat exchangers
if it's basement,
is as follows.
If it's above,
heat
I
flow
understand, but
equals the mass flow
we can try.
Multiplied with
Using the piano window
difference
seems,
of the enthalpy
pretty useful.
Of the fluid used. And for the compressor, it's actually similar. But the compressor does not transfer heat, but does transfer
smokes
work.
maybe. What does he have? Smokes and hard bridge?
But yeah, again,
Breaching charges
similar
of hard bridge.
equation.
Oh, I hope I don't have breaching charges.
The power equals mass flow multiplied with the difference in the enthalpy. I will also put a note here. The heat exchangers are the evaporator.
Thunderbird is using pistol or oscillation.
And the
Do they have the same pistol?
condenser.
Yeah, they have the same pistol.
I guess I never used
Okay.
I've never used pistol, I just know what it sounds like.
Right, yeah.
The
They have Ella, she's running around with her pistol.
transfer
She's a shotgun.
to the
Above where?
fluid
I'm checking your cam.
equals 5 kilowatts.
You guys straight.
How would you then calculate the mass flow in the system?
Possibly broken. This one though?
So again, evaporation equals 5
They just holding the
kilowatts.
ladder jump up, I guess.
And meanwhile, you also know about the first law of thermodynamics for the evaporator. How
Same
would
here,
you
yeah. He's holding the-
calculate
yeah.
the mass flow you need to send through the system? Can any one of you do this calculation?
One down lobby, probably go up.
I'm gonna confuse big window and I'll try and fuse the breach on heaven. Nice. Chill. Using big one or not?
One's on piano.
One piano, yeah, he's 1 HP. 1 HP.
Piano dead. There's one on main bridge, I think.
Cutting the big one now. Could be.
The
maybe
breach
it's
isn't
fine.
open.
Yeah. Oh, that's
Access
one
to
main
the main
bridge.
I don't know what that means.
Main bridge dead.
Yeah, bathroom door. Very low.
How would you calculate it?
I'm planting.
I got
50.
bathroom door covered.
75. Plant down. Could they open?
No wonder we
Read
should
the delta
take a break
enthalpy
here.
and
Run outside
just
and
calculate
be back
more.
in a bit.
Yeah, I'm good.
Yeah. So as I just said, let's consider during the evaporation means during the transfer of the fluid from state 1 to state 2, there are 5 kilowatts of heat exchanged. And now I want to know the mass flow of the refrigerant. How much mass do you need to absorb 5 kilowatts going from state 1 to state 2? How would you calculate it?
Heat transfer divided by the delta in the enthalpy.
Exactly. So it's also shown here in the notes. The heat transferred in evaporator equals 5 kilowatts. And now it's about the calculation of the mass flow. You just need to change the equation, right? It's then the following. The mass flow equals the heat flow divided by the difference in the enthalpy. And this one is 5 kilowatts divided by 1000 kilojoule per kilogram, means 3000, state 2, minus 2000, state 1. 1000 kilojoule per kilogram, right? Exactly. And this one is then 5 gram per second. Okay. Now I would like to know from you, what is the power of the compressor? How much power does the compressor need to put into the fluid, let's say, to transfer it from state 2 to state 3? Who can do this?
Could you subtract the enthalpy at 0.3 from the enthalpy at 0.2, and then multiply that by your mass flow rate?
Exactly. Very good. The power of the compressor is then mass flow multiplied with the difference in the enthalpy, and this equals 2 kilowatts. Okay? Then the next calculation to perform is the heat transferred in the condenser. This is again very simple. Yeah? It's mass flow multiplied with the difference in enthalpy, again 5 gram per second, multiplied with the difference in the enthalpy, 3400 minus 2000. And this then equals 7 kilowatts. How could you how could you calculate the heat transferred by the condenser without knowing the enthalpy difference? How could you calculate the heat transferred by the condenser in an alternative way?
Just add the two previous answers together.
Exactly.
Well, no, the 5 kilowatt and the 2 kilowatt.
Sorry, once again?
Add the 5 and the 2 together.
Very good, yeah. Very good, thank you. This would be an alternative way to just add 5 and 2 kilowatts. 5 kilowatts plus 2 kilowatts equals 7 kilowatts. Very good. Okay. And what comes now into your mind? So if you compare these two figures. Or I can also ask in another way. So if you use an electrical heating, right? So just an ohmic resistance that is where electrical current flows through to generate heat. How much power, how much heat will you receive if you put 2 kilowatts electrical power in it?
So I'm not gonna lie, this is actually really important.
Finally got a code that suits me.
Knew you'd like that one. So, the candles from Mum.
Very simple question, right?
And you get one of your Christmas
Everybody knows
presents
about
early.
the first law of thermodynamics. If I put 2 kilowatt into my electrical heater, how much
Do you not
heat
like?
will I receive?
I think she got you because it's got a B on it more than anything. Oh, very nice. You're going to be smelling very expensive. Go on! Yeah, I thought you might want to.
The answer is very simple, 2 kilowatts, right? You cannot receive more. How is it in this case?
You want cake?
How much heat do you receive by putting 2 kilowatts in the compressor?
It wasn't an easy one. I had to get two different ones. I couldn't just get one and the same. No. Nope.
You will receive 2 kilowatts
Oh,
for the
yeah.
electrical heater, and in this case, you receive 7 kilowatts and just adding 2 kilowatts to the compressor, right? And this one is then the operating mode of a so-called heat pump. Yeah. So actually, the heat pump and the air conditioning are the very same. So the thermodynamic process in it is the very same. But the difference is, where is the gain? The gain of the air conditioning is the heat transferred by the evaporator.
You sleepy?
This is what you want to achieve when using it as a air conditioning system. You want to transfer the 5 kilowatts heat out of the table, let's say, in our example, and get rid of them. This is your gain. And the effort is the power you need to add to the compressor. But if you want to use such a system to heat, to use 8 degrees Celsius cold vapor to heat later on, then the gain is 7 kilowatts and the effort still remains the 2 kilowatts. And as these values are above 1 or more than 100% for the vapor compression refrigeration system, it's not called efficiency, but coefficient of performance. How to judge on the efficiency? This is not a question. And we use the so-called coefficient of performance. It's the equivalent to the efficiency. And this one is gain divided by effort. Now let's calculate the COP of the AC system in this case, and then the COP if we use the very same system as a heat pump. Can you please do so? What is the gain if you use such a cycle as the AC system, and what is the effort? Maybe once again, a quick explanation. So if you consider it as an AC system, then the aim and the gain is to transfer the heat to cool another object. For example, the interior or whatever. So it means the gain is the change of the thermodynamic state 1 to 2. This is the gain. It's the cooling. And the effort is the power you need to add to the compressor to compress the cold vapor. This is the effort. But you could also use the system to gain a cold vapor. So by absorbing heat from the cold environment, for example, you can also evaporate the fluid with cold ambient air and add then the effort, the compression, and then you will receive a hot vapor. And with the hot vapor, you can heat the interior, for example. And I just want to know now, how would you judge on the efficiency? How would you calculate the two coefficient of performance, the first one for the AC system and the second one for the heat pump? Can you please do so? What is the...
It'd be the 5 divided by the 2 for the AC.
Exactly, 5 by 2.
And 7 by 2 for the second one.
Exactly, 7 by 2, very good, thank you, equals 3.5. So this one means, with such a heat pump, you receive 3.5 times the heat than the power you send to the compressor. And now I just want to know, what is the COP of an electrical heater? You should know.
1.
Exactly, 1. Okay, and for which type of car is such a system, such a heat pump now interesting? So for which type of car would you apply such a system to not only cool, but to also heat in the winter time? Okay, once again, what is the efficiency of an internal combustion engine? Does anybody know? Roughly?
30 to 40%.
Around 35%.
30%.
Okay. That's okay, yeah. So it's depending on the operation mode, yeah. Whether it's cold or already warmed up, whether you have a high torque or a low one, whether you have low speed or high speed, and so on and so on. So it depends. But let's say roughly 35%. Let's call it mean efficiency. This means, therefore, waste heat is roughly 65%, right? How is it with the electrical powertrain?
Sorry, repeat that question.
What is the mean efficiency of an e-motor?
It's like 90%, sir.
Yeah, maybe not 90, but let's say 85 or something. Yeah, let's say roughly 85. Therefore, the waste heat is just 15%. Yeah, so and this is why such a heat pump may be of interest for electrical powertrains. Because of the high efficiency, you have little waste heat, and therefore you need to add some additional heating. You need to use electrical heater to warm up the interior, and as the COP of the electrical heater is just 1, yeah. As I said, it might be of interest to use a heat pump instead, because then you receive 3.5 times the heat than the power you added to the system, right? Just one more question: where does the additional heat come from? So if you use the electrical heater, adding 2 kilowatts, you receive 2 kilowatts heat. And in our case, it's 7 kilowatts for the heat pump. Where does the additional heat come from? You know, energy cannot be generated. It can be just conversed and transmitted and so on. But you cannot. The 5 kilowatts must come from somewhere. They are taken from the environment. So the environment, the cold outside temperatures in the winter, they still manage to evaporate this special fluid. Yeah, as you know, for example, it evaporates at 8 degrees Celsius, so you can, or even at lower temperatures. So you can use the cold environment to take care of the evaporation, and then you just need to add 2 more kilowatts in this sample case to make out of the cold steam, out of the cold vapor, the hot one to be then used for the heating. So this is how the system works. And on slide 57, you can see the effect on the range of the electric vehicle. So this one is a study of Fiat, and you can see 3 different ranges in winter time at minus 10 degrees Celsius. So the first one, 147 kilometers, can be achieved if there is no heating at all. So if you don't spend any power for the heating, you can achieve the maximum range, 147, 46 kilometers, but then the passengers will suffer because it's then cold in the interior. Because the waste heat of the e-motor is not sufficient to heat up the interior accordingly. So this is, let's say, the reference value. And if you now go for an electrical heater with a COP of 1, as just discussed, you need to add a lot of electricity to this heater to achieve the required amount of heat. And as a consequence, the distance goes down to 81 kilometers. So just a little bit more than half of the initial range. And if you then consider the application of a heat pump with a COP in this case of 4.5, the range goes again up because you don't need to spend that much power anymore for the heating. And you almost reach, for sure not completely, but you almost reach the reference value for the range. You go back to 125 kilometers range. So this is the effect and the purpose of a heat pump. And for sure, yeah, you don't need it for internal combustion engines because you have more than enough waste heat for such systems. But it could be of high interest, as I said, for electrical powertrains where the efficiency is very high and therefore the waste heat very little. Okay, so I will further beautify this sample calculation and then send to you via the Blackboard system. Then you have for sure the chance to review again and prepare yourself best for the exam then. Are there still any questions for the heating, ventilation, and air conditioning? Okay, then let's move on. Yeah. Also for the HVAC system in particular, the general approach just mentioned today still applies before thinking about or prior to thinking about how you can provide the heat in the best way or also the cooling, let's say. It's better to decrease the demand. To decrease the demand of power for heating and cooling, and there are some leverages for optimization. So first of all, the projected surface and the construction of the windows could be considered. Then you can consider thermal insulation of the body. So if the body is insulated in the best way, then for sure you don't need that much power to heat or cool. You can also consider to decrease the heat capacities inside the cabin. So if you have a lot of material, lots of heat capacities inside the cabin, for sure it requires more power, more energy to heat up or cool down this matter as well. And last not least, so this is also very interesting, the color of the painting highly impacts the heating up of the interior. So here you can see an example for this. So there was a study conducted at 28 degrees Celsius, and then they checked which maximum temperature in the interior might be achieved. And for a black painting, the maximum temperature was 68.9 degrees Celsius. And if you use a white one, a white color, then the temperature is only 32.7 degrees Celsius. So even the painting of the vehicle, even the color, influences the power demand, the energy management of the vehicle. And I think this one can be also experienced quite easy in the summertime. If you enter a black vehicle, for sure it's way hotter than inside than such vehicles with a white color or something. Okay. Now we've already completed the demand chapter, let's say, as mentioned, so we cannot go through everything in this lecture as the time is restricted. So we did not talk about the driving resistances, also not about electrical, mechanical power systems, hydraulics and pneumatics, but we made kind of deep dive for the heating, ventilation, air conditioning. And now we move on to supply to the thermal engines in the first step. Yeah, on slide 60, you can see a so-called Sankey diagram for a gasoline engine, a turbocharged gasoline engine, V6 3-liter engine, and you can see the energy flow for different speeds. Yeah, first one is for 30 kilometer per hour, second one for 70 kilometer per hour, and then the last one for 240 kilometer per hour. And yeah, as already discussed, so for the internal combustion engine, the efficiency is considered to be 1/3, to be like 30 to 35%. For sure, this is not true for every single state of operation, but in average, as you can, for example, see here, for the 70 kilometer per hour operating point, it's even true. 1/3 is used or is gained for the mechanical energy, which means that there are 2/3 of waste. And yeah, for sure, the waste is goes through different channels, let's say, also to the engine oil and so on. But roughly speaking, 1/3 is sent to the exhaust gas, and 1/3 is sent to the coolant of the engine. So 1/3 mechanical power, 1/3 power of the exhaust gas, and 1/3 power of the coolant. Now, question to you: if the engine delivers 100 kilowatts mechanical power, how much waste heat do you generate?
I think 70.
How much?
Sorry, I repeat again. The question again.
Yeah, sure. So if the engine delivers Did you get the question?
I think, yeah, you are there.
Mechanical power. Okay. Mechanical power equals 100 kilowatts. How much waste heat does the engine generate? Simple question, actually. Okay, so if the mechanical power equals 100 kilowatts, then this means 1/3 equals 100 kilowatts. Therefore, you generate additional 100 kilowatt waste heat in the exhaust and 100 kilowatt waste heat in the coolant. So in total, 200 kilowatts of waste heat. Therefore, you need to supply 300 kilowatts of chemical power with the fuel. So the fuel, the combustion equals 300 kilowatts, 100 kilowatt transferred or transformed, converted into mechanical power, and then 200 additional kilowatts, just the waste heat. So really 200 kilowatts, just the waste heat. And how many family homes can you heat with such amount of waste heat? What do you guess? So I would say approximately 20, maybe even more. So to heat a family home, including the water and so on, you need, let's say, 10 kilowatts. So therefore, with such an engine, you could heat 20 family homes. And I think you agree if I tell you that 100 kilowatt mechanical power is maybe not the top edge. So actually, it's a very standard engine, and even such a standard engine already generates that much waste heat that you could heat 20 family homes with it. So this needs to be considered. Lots of waste. And now, in the upcoming chapter, we will step by step, check how this energy flow diagram, how this Sankey diagram can be explained. So we will step by step introduce all the different energy flows to know about the background for it. Yeah? The first step is to review the adiabatic engine for the Otto, for the gasoline engine. And for the adiabatic engine, you only have 3 energy flows. The first one is the actual combustion. This is the heat source. This is the effort you need to take. This equals, let's say, 100%. This is what you put into the system, and what you get out of the system is the exhaust gas mass flow, and for sure the mechanical energy. So this is what you were actually asking for. This is valid for the idealized Otto engine. So there is no friction, and it's an adiabatic engine. There is no more heat flow than the heat flow of the exhaust gas. 100% the heat source, the internal combustion, and then a certain amount the gain, the mechanical energy, and another certain amount the exhaust gas mass flow. And how can you explain that there must be always a heat sink? There must be always some energy transferred without use to the environment. This one is valid for every heat engine. How can you explain? Or let's put it in other words. So if somebody tells you, I've got a heat engine with an efficiency of 100%, what would you ask him for to prove it?
Yeah, I'd ask them to prove it as well, because there's generally some kind of waste, whether it's, like you said, heat, or maybe it's just not efficient. So somewhere along the line, you'll lose some kind of power.
Okay, so the limit for every heat engine is defined by Carnot's efficiency. Yeah, this one can be seen here. So no heat engine can be better than or can have a better efficiency than the efficiency of Carnot. And for the calculation of the Carnot efficiency, you just need to have 2 values. You need to know the temperature of the heat sink, and you need to know the temperature of the heat source. And if you now check this equation, you will recognize that this one can be only 100 or 1 if the temperature of the heat sink is 0 Kelvin, or if the temperature of the heat source is infinite, and both does not apply for existing heat engines, and especially not for our internal combustion engine. So the efficiency of the Otto cycle must be way lower than the efficiency of Carnot, and therefore you have a certain amount of waste heat transferred to the environment again. Let's now check the efficiency of the Otto engine. You can see the equation here. So actually it just depends on two values. The second one, kappa, cannot be really influenced as it's just depending on the substance used, means on the air and then later on the air fuel mixture, respectively the ratio of CP and CV. So this one cannot be really influenced, the kappa, but you can influence epsilon. And if epsilon becomes bigger and bigger, then the efficiency of the Otto engine also becomes bigger. But you cannot increase the compression ratio in infinitely because this one is limited by the knocking combustion. So if you compress too much, then for sure in theory you will have a higher efficiency, but then you will also have a knocking combustion and therefore damages to the engine. So therefore you cannot exceed a certain level. This one means the limit for the knocking depends on the load. So if the engine is running on a low load, you could go for a higher compression ratio in order to increase the efficiency accordingly. But if the compression ratio remains the same for the higher loads, you will then have the knocking combustion, and therefore there are some ideas to go for a variable compression ratio. For example, at Infinity, they have a adjustable crankshaft, let's say, and then they can go for a high efficiency, for high compression ratio, and therefore efficiency when running on low load in the part load operations, or they can reduce the compression ratio, in this case to 8 to 1 when running on a higher load. Yeah, but this is not the standard. The standard is a fixed compression ratio, and therefore, also a fixed efficiency, at least in theory. So we are still talking about the idealized adiabatic engine. Okay, now I would like to know whether you can explain why there must be always heat transferred to the environment, why there must be always exhaust gas of the Otto engine. Can you explain by using this pressure volume diagram? Or maybe let's start more easy. Can you explain the 4 strokes of the Otto engine by using this diagram here? So what happens between 1, 2, 3, and 4?
So are you asking for the working cycle of an Otto engine?
Mm-hmm. So the whole cycle of the Otto engine. So can you quickly explain by using this diagram? So what happens between 1, 2, 3, and 4?
The compression process.
Yeah, where is the compression?
From 1 to 2.
Mm-hmm. Okay. So from 1 to 2, there is the compression.
Yeah.
So where does the energy for the compression come from?
From the previous stroke or the motor, the starter motor.
Yeah, exactly. So when you are about to start the engine, the energy comes from the starter. During operation, the energy comes from different cylinders, which are currently working, or it's taken from the flywheel. So this is why you maybe need a flywheel, at least for a 1-cylinder engine, to have a mechanical energy storage to be able to provide the energy for the compression to go from, let's say, 1 bar up to a higher pressure after the compression. So what happens between 2 and 3?
That's working stage.
No, that's wrong.
Spark plug ignites the charge. The pressure rises at constant volume.
Yeah, exactly. So this one is then the internal combustion. So this is where you actually add the heat to the system. This is the heat source. From 2 to 3, the combustion takes place. You add the heat to the system. This is the heat source. The goal is actually not to increase the temperature. This is just a side effect, a negative side effect, let's say. But the goal is to increase the pressure, to go for a higher pressure. And then you have a pressurized gas, let's say, and this one can be used to be expanded. And then the working cycle follows, the expansion from 3 to 4. Now you can see in the diagram that in the stage 4, the gas has still got a very high pressure. You can see on the y-axis, and you can see by this remark here that the gas also has got a very high temperature, but is anyway released to the exhaust system. So this is then the pressurized and hot exhaust gas. And my question to you now is, why is it like that? So why can you not expand to a low pressure and use the whole energy in it? Because you can imagine if you release this hot gas, this hot pressurized mass flow to the environment, for sure you lose the energy, right? So why can you not use the remaining pressure? It's very important. This is fundamental of combustion engine, let's say.
If we want to use the whole energy, the stroke would become very large.
Yeah, exactly. So the reason for this is, so if the expansion stroke, if the working stroke has got the same length, let's say, as the compression stroke, then for sure the pressure and also the temperature must be way higher afterwards. So because you're starting at a much higher pressure, at 90 or maybe 100 bars, but you have got the same length to expand because the compression ratio is fixed by the crankshaft. And for sure you cannot reach 1 bar when starting at a very high pressure with the same length of the expansion stroke. So this is the reason for that. And even so, you would manage to expand way longer, to go down to 1 bar, yeah? Then still the temperature would be very high. This is how you can explain why the efficiency of the Otto engine must be way lower than 100%, and why there must be a hot exhaust gas still remaining after the working stroke. So this is fundamental to the internal combustion engine, and this is the first step towards our journey to the actual Sankey diagram. Yeah, so after this chapter, you will know how these different energy flows are actually created. And the first step was to review the adiabatic engine, where there are only 3 flows: the heat source, the effort, the internal combustion, and the gain, the mechanical energy, as well as the heat sink, the exhaust gas mass flow. So please consider how to explain that a heat engine has got an efficiency lower than 100%. This one can be explained with the efficiency of Carnot. And please also consider
how to explain why there must be a hot and pressurized exhaust remaining after the working stroke. Okay, if you now want to go for a, let's say, longer working stroke than the compression stroke, there are two options to take without changing the crankshaft or something like that. The two approaches are the approach of Atkinson and Miller. Yeah.
The approach of Atkinson is to remain the intake valve open still during the compression stroke. So by doing so, the pressure starts to rise a little bit later, because in the beginning of the compression ratio, the compression stroke, the intake valve is still open, means you cannot increase the pressure because the air will flow out again. And then it rises a little bit later. It rises a little bit later. So like here, for example, yeah. And as a consequence, the working stroke is longer than the compression stroke. This is the approach of Atkinson. And Miller went for another approach, as described here. The inlet valves close very early before the bottom dead center of the piston. The intake stroke is therefore shortened, and the bottom dead center passed through with negative pressure. So this would be another option to make the working stroke longer than the compression stroke, and to therefore use more of the energy added by the internal combustion. Okay, let's move on to slide 67 and do a more deep discussion about the heat sink, about the exhaust gas mass flow. So actually, it contains three elements: the pressure, as just discussed, the temperature, and the air pollutants. Yeah, the pressure is needed for two things. Yeah, the first thing is to overcome the flow resistance of the exhaust system. So even so, you would have the chance to go down to the ambient pressure. You could not do, because you still need a remaining pressure to overcome the flow resistance of the exhaust system. This is the first thing to mention. And the second thing, which is more valid in terms of energy for sure, you can use this pressure gradient towards the environment to make the turbocharger run. So you can maybe not use this energy here by the crankshaft itself, but you can use it to operate the turbocharger. The turbocharger uses the remaining pressure after the working stroke. Then the second thing, as mentioned, is the temperature. The temperature of the exhaust gas may be used for waste heat recovery, which is then discussed in chapter 5.4.2. And again, there are still remaining air pollutants in the exhaust gas mass flow: unburned hydrocarbons, carbon monoxide, nitrogen oxides, and particles. And this one are sent to the after treatment. And in order to make the exhaust gas after treatment work, you also need a certain level of temperature. So therefore, the temperature could be also considered as somehow used already in the system. Okay, so by the way, why do you need an exhaust system? So why do you not just release the exhaust via the valve? Why do you really need an exhaust system? What is the reason for that?
No, the engine doesn't overheat and explode.
Yeah, but again, so you could just release the exhaust gas through the valve, yeah, to the environment again. But why do you need an exhaust system?
And is it to get rid of the pollutants in the system which will corrode or damage the engine?
Mm-hmm. So there are several things to consider for this. Yeah, so the first one is that you need to get rid of the heat, yeah, as you just mentioned. So you cannot just release the heat in the engine compartment because everything would overheat then. You really need to take care that the heat is properly released to the environment without any damage to the surroundings. This is why most of the exhaust gas systems end at the rear of the vehicles, but you can also use some side pipes, for example, or you could also release the hot gas to the top. At least it must be ensured that the hot exhaust is far away from the vehicle afterwards and cannot damage it anymore. Then for sure, there's also some noise dampening function of the exhaust gas system. So if you would just release it in the engine compartment, it would be just too loud. So the noise dampening is very important as well. And last but not least, the whole exhaust gas after treatment is included in the exhaust gas system. So these are the three main things to know: that get rid of the heat, damping the noise, and taking care of the exhaust gas after treatment. Okay, yeah. Then let's talk about more realistic engine. So no more the idealized Otto cycle to be discussed, but a two-stroke chainsaw in this example here. And what you can see is that for sure the efficiency, the mechanical energy went down in comparison to the idealized cycle. And then we've added another energy flow, the energy flow of the air cooling. So the adiabatic engine just discussed without any wall heat losses is not feasible due to unpleasant effects on the rigidity of materials. So it would be just too hot. Again, uncontrolled self-ignition and volumetric efficiency. So this is why you cannot really have an adiabatic engine. This is why you always need to cool the engine. This is the first change to the diagram here, and the second one is you also need to have a lubrication. And in case of the two-stroke engine, you cannot have an oil sump or something like this. You need to add the engine oil, the lubrication, to the fuel, which leads to the fact that later on in the exhaust gas, you also have the internal energy, the heat of the engine oil included. So these are the changes to the flow diagram so far for the air-cooled two-stroke chainsaw engine. Yeah, what are the advantages now of the air cooling? Yeah, for sure, it's cheap, it's light, you don't need any special components, it's robust, and you can also flexible move. So if you consider a water cooling, for example, yeah, it would be not that easy to go for overhead operation because of the distribution of the coolant then in the whole circuit. So there are some advantages of the air cooling, but also limits. Yeah, for sure, the limits are the size, the available space. So if you want to transfer more and more heat for the cooling to the environment, yeah, you need very big fins here, and those require a lot of space. Then you've got the risk of contamination. So in between the fins, yeah, to ensure the cooling, there might be some dust or whatever accumulated, which then reduces the heat transfer. capabilities of the air cooling. Another limit is given by the production technology. You cannot just easily cast very, very big fins. So there is a restriction for this. And last but not least, there's almost no cooling when idling. When the vehicle is standing still, then there is for sure no airflow. And then you also have almost no cooling when you apply the air cooling then. Okay, so even so, for passenger cars, the air cooling, the direct air cooling is no more relevant. This one is still in use for motorbikes. So especially for BMW motorbikes, you still have some air-cooled engine, which is quite feasible for those because there are some boxer engines. And as you can see here on the picture, for the boxer engine, you have a very, very good circulation of the air, because the engine block and the cylinder head, they are actually directly in the airflow. And again, if you then go for some fins, as can be seen even on the screw for the exhaust gas manifold, you are able to transfer the required amount of heat to the environment. For sure, this is no more state of the art for passenger cars. I will explain the details, the background for this later. But there are many other components in every vehicle which still need the air cooling. So, for example, control units are air cooled, as shown here on this picture, but also headlights, for example. Headlights, which might be also very hot during operation, are air cooled, and sometimes they even have a separate fan inside the headlight to ensure the required airflow. And then there on the right side, again, another example for air cooling. This time it's not for the cylinder head or engine block, but also the oil sump of some engines might be air cooled, might be with some fins on it to ensure the cooling. Okay, now let's talk about some general tasks of lubrication fluids. So it's not only the lubrication of components with a relative movement against each other. There is some more to mention. So the lubrication for sure also takes care of the cooling. So for example, the piston bottoms of internal combustion engines or the turbocharger is cooled by the engine oil. Then it must ensure the right sealing between piston and cylinder tube, for example. Load transmission can be achieved by lubrication fluids, such as for the variable valve train. Next one is vibration damping. For example, the drivetrain dampers, they use the oil for the damping. Cleaning, also very important. So the engine oil takes lots of ashes and abrasion of the engine, which are then separated in the filter. And last not least, also rust protection of metal components, for example, within the oil pump, is an important task of lubrication fluids. And in order to be able to perform all these tasks, the oil must be kept in the required thermodynamic state. Means must be kept in the optimal temperature range to have the right viscosity, to be still stable, to have the right thermal stability, and so on. So this is major task also of the thermal management to ensure that the lubrication fluids, the engine oil, for example, is kept in the optimal temperature range. Here we have another example for the application of oil for propulsion, actually. So maybe you know that the Fendt Vario drive. So this is a heavy-duty truck, let's say, for agricultural applications mainly. And for this vehicle, the system works as follows. So there is an engine to not only power the rear axle, but to also power a hydraulic pump, which then generates high pressure in the hydraulic system, and later on this one is used to power hydraulic motors, and therefore this vehicle has got a lots of oil in the propulsion system. So 90 liters of oil just for the propulsion, and almost 140 liters for auxiliary consumers such as the hydraulic fan, and almost 50 liters of engine oil. So for sure for motorbikes and passenger cars, the numbers are not that high, but as mentioned, from time to time we can make a short excursus to also review different vehicles. Okay, we were just talking about the two-stroke air-cooled engine, and now we add another energy flow to our Sankey diagram. It's the energy flow of the engine oil. So for the two-stroke engine, as I said, the oil is emitted by the exhaust, must be refilled then, therefore as well, and for sure you cannot meet the latest regulations regarding the limits for air pollutants. This is why in state-of-the-art engines you have a closed circuit for the oil. Means you need to have pipes, you need to have a pump, a filter, a cooler, and so on and so on. And even so, this one is still an air-cooled motorbike. There is a radiator in front, but this one is for the engine oil. So this is the next difference to the very simple two-stroke engine. And another one is that the exhaust gas or the exhaust system contains a three-way catalyst to convert all the air pollutants. Okay. Let's move on. Here you can see an example of a closed engine oil circuit. You can, by the way, also see the influence of the oil temperature to the friction. So starting with an oil temperature of 20 degrees Celsius, going up to 110, the desired temperature, you can reduce, or you must on the left side, you can see the layout of such an engine oil circuit. Basically the oil is sucked here from the sump on the bottom of the engine, sucked by the oil pump, and then it's sent through the oil filter to get rid of all the abrasion and the ashes and so weiter collected inside the engine. And in the next step, it's sent to the radiator where it's cooled down. And then the cooled down oil is used to go to do the lubrication for the crankshaft, as mentioned, to cool the bottom of the pistons, and for sure to also do the lubrication of the valves, the valve train, and so on. So this is how the general layout of the closed oil engine oil circuit looks like. As just mentioned, the oil is also used for the cooling of the engine, and there have been even oil-cooled engine, but unfortunately the mass density, the specific heat capacity, the heat transfer coefficient, the thermal conductivity, and so on of the oil is comparatively low of the engine oil as in comparison with water. and as a result, you can only transfer a very limited heat to the oil. Therefore, if you would go for an oil-cooled engine only, the power density would be also lower. But there are some advantages. Yeah, by using the oil, there is no corrosion, there is no cavitation, and there is also no freezing. So for simple engines, for motorbike engines, for example, such a oil cooling can maybe still meet the requirements, but for sure not for high sophisticated passenger cars. Okay. Yeah, now let's talk about the exhaust gas after treatment. Most simple one, three-way catalyst. Do you know why it's called three-way catalyst? Anybody know? Are you still there?
Yes.
Yes, sir. Great. So why is it called three-way catalyst?
It works on 3 different pollution molecular.
Exactly, yeah. Because the three-way catalyst takes care of the conversion of 3 different air pollutants of carbon monoxide, unburned hydrocarbons, as well as nitrogen oxides. Yeah, and in order to do so, this one can be seen on the chart here, on the graph on the right. It must be kept again in a certain temperature range. So this one is between, let's say, 210 to 300 degrees Celsius. In this temperature range, the conversion rate is maximum, and this is why you want to really reach it very quick. And after cold start, there are several measures available to reach it. Yeah, the first one is to change the ignition to late. Yeah, to have a late ignition, which leads to high exhaust gas temperatures. Another thing to do is to go for fuel mixture enrichment. Yeah, to go for more fuel than needed for the actual combustion, in order to have more unburned hydrocarbons in the exhaust gas. And if you then blow in additional air by the so-called secondary air injection system, then you have another combustion in the exhaust gas, in the exhaust system, which leads to a quick warm-up of the three-way catalyst then. And last not least, you can also go for electrical heating of the three-way catalyst in order to reach this temperature as soon as possible. But for sure, all 3 things just mentioned decrease the efficiency of the engine or increase the demand of electrical power, and both of it lead to a higher fuel consumption as a consequence. So therefore, for sure, the aim is to spend as less energy needed for the warm-up of the exhaust system, and this is why the exhaust system nowadays are most likely thermally insulated to keep as much energy inside the exhaust and to not lose to the environment, and to then, as I said, also warm up the after treatment system as soon as possible. Here you can see the behavior in the NEDC for a 3-liter gasoline engine. So the yellow graph represents the temperature upstream the catalyst, and the red one downstream the catalyst. And as you can see in the beginning, the temperature downstream is below the temperature upstream. So the whole system first needs to heat up, but afterwards, when everything is heated up and when the conversion of the air pollutants is going on, then you have a globally exothermic reaction, and therefore higher temperatures downstream the three-way catalyst than upstream. Okay, yeah, here you can again see the system layout of the secondary air injection. So the air is taken from the air filter, sucked by a pump, and then sent via a valve to the exhaust gas manifold actually. So you can also see it here in this picture. So you blow actually additional air to the exhaust gas, to the exhaust gas with still some unburned hydrocarbons in it for sure, yeah. And then you have an additional combustion in the exhaust gas system to heat up the catalyst, yeah. And the effect on the emissions can be seen here. So if you don't go for such a secondary air injection, you will have very high cumulated emissions, represented by the two blue graphs, and yeah, by applying.
Sorry, sir.
Yes.
This secondary air injection, you mean turbocharger, right?
No, I mean what I just explained. So this has nothing to do with the turbocharger. But as I said, yeah, if you want to heat up the three-way catalyst very quick, yeah, you can go for a fuel mixture enrichment. You can inject more fuel than you need for the combustion inside the engine, which then leads to unburned fuel in the exhaust gas, and then you blow additional air into the exhaust system in order to have a second combustion in the exhaust system in order to heat up the three-way catalyst more quick, right? This has nothing to do with the turbocharger, actually. Some more questions? Okay, yeah, and again, yeah, to keep as much energy inside the system, especially when stopping the vehicle on a high temperature, to conserve this high temperature for the next cold start, not only the exhaust system as just mentioned, but also the whole engine is more and more isolated, yeah, to keep the energy in, as I said. For example, the BMW Syntac Synergy thermoacoustic capsule can maintain significantly higher temperatures for up to 36 hours, and this then helps after the next cold start to reach the temperatures more quick. Okay, next thing to add is the energy flow of the coolant circuit, but I think we went through all the chapters very quick today, and this is why we can also stop the lecture for today and then continue tomorrow. Okay?
So I would like to ask, can we get the recording tomorrow? It's left. Shit.
It's gone already. It's gonna ask if you can get the slides. He's not gone already. He's in there.
No,
So that's the slide.
Oh,
The
so
slides are online, right? On
yeah.
platform.
Speak about tomorrow. Can we make sure that it can be recorded so we can go back for it?
Yeah, I check it, okay?
Okay.
So
Okay, thank you very much. Yeah, sure. Once again.
could we also get the a copy of all the slides as well?
It's in Blackboard.
Oh, sorry.
Exactly. The lecture notes are available, okay?
Lecture notes and learning materials.
Connected.
Awesome.
Channel
Thanks.
switched.
Okay, so thank you very much for listening today, and then I'm looking forward to meet you again tomorrow.
User joined
Bye.
your channel.
Yeah,
Bye bye.
thank you.
Bye, sir.
Thank you.
Bye, thank you.
Hello.
Hello.
Go on. What you doing?
What do you mean?
What? Come on. What you doing?
What do you mean?
Well, what you doing?
What do you mean? What? What do you mean?